Good afternoon, good evening, good morning. We are live. It's been a minute. I have been sick, but look at this. The snows are falling. Here is Fuji. I was eating some snacks and I made my coffee, but look at the roof of this building. We're snow covered here in Boston. And I wanted to share this with you. So I'm gonna set you down over here and then I'm gonna go get my coffee and I'll share the live and hopefully we can do a nice chat today. In fact, I could stay right there. You could stay right there. Look at these chairs. Look at the yard, it's snow covered. Wow. Okay, this is not working out as well as I thought it would, but that's okay. There. Snowy. Baji and Suji have gone to the upstairs bedroom. It's warmer up there. We might actually follow them. But for now, I wanted to show you this site. I'm gonna get my coffee and share the live. Fuji's down here with me. Thank you, God. Fuji is so nice and giving me company in the living room and kitchen. Look at that. Oh, I see with my eye. I spy with my little eye a Baji. Oh, Baji. Baji has come down. Hello, welcome, welcome. Welcome to the live. I'm still recovering, so you might hear my cold. But here we are. Hi, Baji. Hi, Baji. Hi, Baji. It's so snowy. It's so snowy. Hi. Hi, Tanmeep. TNMYP. Hello. Hi, Baji. Look at all the snow outside. Hi, Marilyn. Hi, Kraz. Oh. Hi, Victor. Hi, B-Folks72. Hi, Nell Smorga. I can certainly try to read Spanish. I think I understand quite a few Spanish words, actually. How's your day going? It's such a snowy day, Marilyn. How are you? Thank you, Tinmip. New Year. Yes. Happy New Year, everybody. Almost. Thank you so much. Your cat is cute. Thank you. Thank you, B-Folks. Thank you, Nell Smorga. Thank you, Tinmip. Thank you, Victor. Ooh, Victor Manuel Martinez. B-Folks72 says your cat is cute. Thank you. Marilyn, Happy New Year. Show your beautiful face, lady. Thank you. The A. I love that cat. Hi. Hi, cool kid Carter. Both of your cats are cool. Thank you, Marilyn. There's actually even more cats than you've seen, Marilyn. You'll have to wait and watch. Baji, are you gonna show some tricks? Look at Baji serving his kingdom, his very snowy kingdom, like the Lion King. Dun 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 dun. Hi, Baji baby. Oh, Baji. Martinez. Victor says, ha ha ha. Thank you, Victor. Marilyn says he's doing tricks. B folks, they're of a baby age. He's a baby. Baji Baba. Baji baby, look at the snow, Baji. Is it snowing? Yes, it is. Look at these chairs. They're so covered in snow now. Baji, the snow is like your chest. It's white. But Baji has a hint of pink and grayish or silverish. He's doing tricks. I got 4 cats, but one of my... Oh no. Oh no. They got kicked out. Oh, we're so sad. That's a sad news. Baji! So there is a sister of Baji upstairs. She is enjoying the warmth. The upstairs has very low ceilings because it's basically the attic converted to a bedroom. And oh, Baji, there's something on your eye. Sorry. Well, near your eye. So the downstairs has taller ceilings, so it actually kind of stays cold down here. It's not as easy to warm it up. So one of these kitty cats, she's so clever. She knows where it's warm and she stays up there mostly. Well, she comes down too, but she's actually trying to influence us to go upstairs. Marilyn says it's because he peed on the bed. Look at this. Oh. Well, I think Baji has peed on the bed once, at least. Baji, was it you? I couldn't tell guys. I was at work and I come back and somebody had peed on the guest bedroom bed. And most certainly I thought it's probably Baji. I did think it was Baji. I don't know if I was fair in this assessment, but I did see him. It was based at least partly on certain evidence because I saw him kind of scope out this particular blanket that was on the bed. It was a weighted blanket, sort of for like anxiety. You know, I bought it with a lot of money, secondhand from a neighbor when I used to live sort of in the apartments before this place. And it was extremely heavy. Of course, that's kind of the point of it. And Baji thought that the little holes in this anxiety blanket would be lovely to kind of use as I don't know, like a pee hole or something. And he thought that the texture was just right as a second bathroom for him. And so, hi. Hi, Smirky Ace. Hi, Feliz. Bagchi. Hi, Marilyn. Thank you for subscribing. Really appreciate it. But anyways, that's how Baji, I believe, came to subscribe, or not subscribe. I was reading that word subscribe. He peed on a bed as well, but he doesn't usually. Thank you so much. Can everybody please like the live too? Thank you so much for subscribing. Thank you for being here. Marilyn says that she subscribed. Thank you. Smirky Ace, hi. How are you? My voice is a little low because I'm still recovering from a cold / flu / whatever. It was pretty rough. But here we are. We're live. Here is Baji, baby. Baji, do you want to hold the phone? Do you want to hold the phone? Oh. Don't edit yet. No, I'm not. We usually stay live for a while. Ooh, Baji, let me clip this. And look at the snow. It's, I don't know if you can see the snow falling as well as I can because the little particles of snow that are falling constantly, it's hard to see, but look at that. Look at this tree. It's pretty. Look at all the snow on the chairs. And it's building up. It's sticking a little bit because it's a little wet, I think. So sometimes when it snows and rains, like it washes off. But this one is, hopefully it won't be too icy on my stairs up front. Last time, well, earlier this year when it snowed because of the winter, earlier this year, like January or so, you wouldn't believe what a death trap the staircase or the stairwell outside my house became. Like, it was so full of ice, like I couldn't touch anything. The railing is like slippery and wobbly because we need to repair it and we haven't. And it was freezing cold and icy. Each step had a layer or 2 or 3 or 4 of ice, and all these like icicles just hanging out everywhere. And I started to slip and fall. And then I somehow managed, and on the way back from work, I had a really heavy bag with me, and I was again slipping and falling. And I was like, oh my gosh, I don't think I'm going to be able to go up the stairs. Like, I can't do it. And out of nowhere, somebody came that I don't even know. I think he was a neighbor, and he saved me. And he took my bag and he gave me his arm and he helps me up the stairs. And that's how I got home. So that's the story of that. Marilyn says, I just got done eating. Good job. So thank you to that neighbor who helped me. But this was the little story of the time. Here, this is a Christmas story of kindness. Because it's almost Christmas, we will share some of our stories that are kindness related and maybe even ice and snow related. Oh gosh, Baji, did you almost fall? But kitty cats always know to catch their fall. Fuji, are you okay? Oh, my baby, my baby. My baby Fuji was sneezing a moment ago. I'm sorry, Fuji. So anyway, it was very kind, and I didn't even know him. And I haven't really seen him since. I think he's a neighbor. I'm not even sure how he knew that I was struggling. I might have let out like one small scream, but I don't know exactly where from he came. And he helped me though. And it was nice to get a little bit of reassurance and help because I was just mainly, I think, feeling like, oh my God, this sucks, and I'm struggling and feeling a little bit very discouraged in that moment. So it was very nice to get the help. What are you talking about? Hi, Rary. Hi, Life Good. Hi, Rary. I'm talking about the time when I almost fell on some stairs outside my house because they were freezing and full of ice and snow, and I was slipping, and some stranger helped me. And it was very nice of him. Thank you. Thank you, universe, for sending the stranger who was not a danger, but a help. That's all. How are you? And here is Baji, and here is a snow day. Little Baji. And look at this. So much snow outside. I mean, Boston has gotten more snow than this, typically, but I don't know exactly how much we will get today, but it looks like it's sticking. It's a little bit wet, and it's not raining and washing away, so here we are. Here. I'm gonna sip my coffee too. because I made, ooh, look at the little picnic table. Isn't that so cute? I love our picnic table. Oh, I mean, we barely use it, but covered in snow, it looks kind of nice. Oh my gosh. Ooh, I think you can see the snow better like this, right? Zoomed in. Wow. My grandma had been on the phone because there's a million people calling. Oh. Is everything okay? Hi. I see. Phone is busy. Actually, yeah, I'm using a phone too. It would be bad if somebody called me right now. I think I can make it go away though. Oh yeah. Yeah, I just checked. Good thing you reminded me to check. My phone is on Do Not Disturb when I do the lives so that people can't call and interrupt. So I usually put my phone on silent and Do Not Disturb, and people can still text me and I can still see if they need to reach me. But that's, oh my God. Somehow I really like watching the snow from inside. Obviously, while I'm inside, because it's not as nice to kind of drive around in it or walk around in it. Oh, hi, Baji. Hi. Baji's on my lap now. Look at this. Baji, Baji. Oh, Baji. Come. Come. Lap time. Lap time. Oh. Oh. Little Baji, baby. Baji, where's your face? I usually play Roblox too many times that sometimes, look at Baji, he wants attention now from Fuji. Baji just really loves attention. Thank you, everybody. Please do like the live. Let me read your comments. I usually play Roblox too many times that sometimes Roblox delete by itself and I can't get on. Oh, really? You will find some other people will join the live in probably a little bit of time, and they all play Roblox. So this is quite a theme here on my live streams, actually. Like, there's a lot of people, a lot of little kids and other people too, who play Roblox. They all seem to like Baji and the kitty cats and video games and Roblox, and we usually have a nice chat together during these lives. So I'm having some sips of my coffee. I have to be careful about my voice too, because I've been recovering from a little illness here, being sick, but I'm happy that we're all here and chatting and hanging out with the kitty cats and the snow. Baji, are you enjoying the snow? Oh, look at Baji. He's watching the snowfall. gosh. Okay. I'm gonna get under covers. More covers. When you leave your coffee out too much, it'll melt your cup. Oh yeah? Look at this. Isn't it cool to see rooftops with snow on them? You're so cute, Baji. Okay, let me go get my cup. Hi, Baji. What do you look like? Thank you for liking the live. Marilyn, we will see what I look like. And thank you for this comment in maybe Arabic. Thank you so much. Really appreciate it. Really appreciate it. I can't quite read it though. And thank you for liking the live. Baji. Baji, are you trying to find something like human food? No, no, no. Let's not do that. Let's see. I think I'm gonna leave these out. I have peanut butter. I have honey. So I have been sick and not been able to show you guys the Christmas present I got from the sponsor of my live here today, Spot Mart. Baji. Do you have Roblox? I do not have Roblox. Do you want to tell me how Roblox is played? So I'm supposed to be like putting this jewelry on and showing you guys and telling you about Spot Mart, who is going to be the sponsor of a few of my lives and videos. But I've been so sick. I haven't really been doing my normal live streams quite as normally. And today I thought I will go live and show you the snow. And I'm still kind of recovering. But in a minute here, I think I'm going to put this jewelry on and finally kind of get it over with, get it done, show it to you guys. So they just mailed me this jewelry. I'll link it later on in the live description in case you're interested. But look at this. They sent me a pendant which has B in it. Oh my gosh. I think it's B for Baji. Wow, Baji, because of you, I got a B for Baji pendant. Maybe B for Big Bang. Because we also talk about the universe and the Big Bang So it could be any of these reasons, but we got a B for Baji pendant. All right, I'm gonna finish my coffee and then I'll put the jewelry on. Do you have Roblox? I don't. You usually start out your account and then you type in your name, but your real name, not your real name. And then you get it in there. Pick a boy or a girl. Only has to be a bacon. It only has to be a bacon? A bacon? What does that mean? A bacon? But yeah, guys, thank you for your patience. My throat has been bad. I've been coughing and I've had a cold and I've been sick. So I'm sorry if the lives have been a little bit different and you've been hearing my coughs. And I haven't been able to do my usual long physics teaching type of lives. Sorry about that. And thank you for joining. Thank you for joining the live stream. Welcome to you. And also thank you for watching this later on, if you're seeing this later as a video upload. Really appreciate it. Thank you. Oh, look at Baji Baba's little eyes are closing. And here's the snow falling. Here's the snow falling. You know how like when you're sick, you don't really feel like doing things? That's how I've been feeling. I just like don't want to do much. I want to rest. But at the same time, I did do a few lives and I did like do some things. But then I'm like, oh, but I'm not being able to give my 100%, and that's okay. I needed to prioritize self-care and health. Let me write a message. Oh, wait a minute. I never... Hi! Dora Dora! Whoa, a stream that isn't in the twilight hours of night. I know, right? I think I'm gonna do more live streams that are in regular hours too, just because I need to like rest more and I'm getting sick and it's so cold, and being downstairs here where I do the lives, it's kind of hard to do that when it's so cold and in the nighttime. So you might see me more during a more earthly hour. But at the same time, some of my friends are saying that I am like AI and they think that I am like awake all the time. You never know. You never know at what time you'll see me. It's like 4 p.m. Cool. Good to hear. You probably are nonstop awake. College taught me nonstop coffee is the way to go. I know, I'm up a lot. It's only 3:02 in here. Wow, Marilyn, are you in Central Time? We're on Eastern Standard Time. Boston. This is the Boston snowy day. Doro Doro, are you done with work? Or are you on like a vacation now, like the holidays? Tell me, you guys who are working, what are like your holidays and hours and stuff? Accordingly, I'll do my lives and things like that too. Well, my lives have been different because I was sick, but yeah. I'm done with work for the week. Monday is my last day before a week off. Okay, good to know. That's what I thought. I think I'll switch up my hours to be a bit earlier during the Christmas week because I feel like people might be off of work, you know, and things like that. So I think I will shoot for more of the afternoon and evening time instead of like the dead of the night time. When are you going to stream next then? I go live on most days. So Marilyn, you should I think you already subscribed, but yeah, subscribe and put the notifications on so that you're notified when I go live. Thank you. Heck yes, cool to hear. Thank you, Doro Doro. So Marilyn says you're hacking. Okay, good. So I think we'll be live. We'll be live again tomorrow, probably. Maybe around the same time, actually. I hope my voice gets a lot better by then and I can get back to more of the physics topics and things like that. I think we'll do some reading and learning today as well, though. So worry not. Oh, thank you. I love you and your channel. Thank you so much. Yay. Really appreciate it. Thank you. Okay. All right, guys. I appreciate your patience. I might have to put that jewelry on. The thing is, I told the sponsor I would, right? So I kind of got to do it, okay? So don't go anywhere. After the jewelry, I will get back to the regular chat and topics of discussion here. So don't you worry about that. Look at this site though. It's like the sun is about to set. I'm hanging off a cliff. What? The sun is setting and it's like this blue hue is happening outside with the snow and the oh my gosh. First of all, look at how fast the sun sets in Boston. It's like 4:06 p.m. Sun is already setting. And it's still snowing. Ooh, look at it. There's a FedEx truck right there. It's Christmas and FedEx is here with our presents. Actually, Santa is just FedEx. So Look at the snow. It like actually snowed today. It actually snowed. There's snow on things. There's kitty cats. Rudolph the red-nosed reindeer had a very snowy day. Baji. Baji's looking at his robot toilet. Baji, please don't interrupt the cycle. We want your things to be cleaned. Rudolph the red-nosed reindeer had a very shiny nose. La 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 la. Hi, it is I that has been speaking this whole time. Spot marked gold earrings for women. Okay, I already showed you that one. Let me show you the other set of jewelry that they sent me. Rudolph the red-nosed reindeer had a very shiny nose. And when Rudolph wanted to play with the other reindeers, I think they pretty much all said no. And that's how we know that Rudolph was very, 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 very unique. And then Santa came to Rudolph. And told him that he was a cute reindeer. It's Christmas! I can't scream too loud because I have been sick. Rudolph the red-nosed reindeer had a very shiny nose. Can anyone say the words after that? Because I am not very good with the lyrics of this thing. Da 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 da. Christmas gift from Spot Mart. Okay, let's open this. Ooh, Spot Mart bubble letter necklace gold bead made in China. Sponsor of the live today. Oh, look at Baji. B for Baji is here. Rudolph the red-nosed reindeer. How do I open this? And then Rudolph cried so much that no one would play with him. Wow. Ooh, this chain is thick. Fuji. Fuji wants to see. Oh, Fuji. Oh, it's for you. It is for you. Fuji thinks. No? No? What do you mean? No what? Oh, look. Nice push. Nice little... Nice little earring. Look at that. With a push and everything. Oh, I'm sorry. Are you mad at me for singing it wrong? You can tell me the words. I'll sing the words. Baji the silver kitty cat had a very shiny earring. Look at this. These are the earrings. La 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 la. I'm so sorry, guys. Tell me. Ow. Where's my ear piercing? Okay, this is gonna be rough actually, because I don't wear earrings very often. Oh, there we go. It worked. There we go. It worked. I was a little nervous. I don't wear earrings often enough. Like sometimes I feel legit my piercings might be closed. I have been sick, you guys. Therefore my voice is kind of weird. And I am wearing this jewelry. And the sponsor will be very mad if I don't. La 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 la. Please do bear with me. Oh, sparkly. And he pooped and pooped. Sparky. Sparkly. Sparkly. Ooh. Okay, sparkly and sparkly. Rudolph the Red-Nosed Reindeer. This is pretty heavy. When it was in the packaging, I didn't think it was that heavy. This is called Spotmart, S-P-O-T-M-A-R-T. They're online jewelry, small decoration, big style. You can order online. I'll have a link in the description. This is pretty heavy. B for Baji. B for... Baji's looking at it, knowing fully well that it's his. This is a pretty heavy necklace chain thing. Hi! Hi, Marilyn. Welcome, everybody. Welcome, everybody. How are you guys, everyone? There's only 7 people? What do you mean? Gypsies, 7 dwarfs. There's no such thing as only 7 whole people. Okay. All right, this is gonna be a little bit hard. Oh, there we go. Oh, I got it in. I got it in. I got it in. Rudolph the Red-Nosed Reindeer. Not bad. Baji, look at this. Baji. Oh, Baji. Baji, look at your pendant. Baji. 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 Oh, Baji Wawa. Baji. 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 Baji likes it. Okay, so you guys. We breathe in and we breathe out. I've had some trouble breathing, guys, because I've had a cold. Now there's 5. They keep changing. I need to blow my nose, and I'll be right back, okay? I mean, I'll still be here. Once again, thank you to Spotmart for the amazing sparkly earrings and pendant chain. What is this product called? It's called... Wait. It's on here. No. It's called Bubble... Bubble letter necklace. Bubble letter necklace. B for Baji. Okay. Oh wait, I should have clipped this whole thing. I should have clipped this whole thing. There, I clipped it now. Okay. I think we'll talk about something something interesting in just a second here. Once I go get my saturation saturated with my nose. BRB. Here, look at Baji. 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 Okay, what shall we read today? Oh, I know. I think I'm going to read about particle astrophysics from my own thesis. So that's what we'll do today. We will get highly settled with tea, coffee, snacks, and then we will read about particle astrophysics from my thesis. So I'm gonna go get my laptop and do that. Hi. Lee. Changing? It's making me lag on my phone. Okay. Rudolph the red-nosed reindeer had a very shiny nose. And if you ever saw him, you would even say it glowed. I used to stream, now I don't. Hi, I'm back, battling my worst sickness ever. I have also been sickly. Oh, that sounds awful. Yeah, no, that sounds awful. You and me both. We've been so sick, but here we are. Here we are, and I'm gonna go get my laptop, and we're gonna do a particle astrophysics chat today. Yay! From my thesis. Lee, are you ready for some chats and some interesting topics? Lee, are you ready for some chats and some interesting topics? Okay, good. All right, and look at this bubble B for Baji necklace that I'm wearing. My phone texts and I stop texting at the same time. Good job, Marilyn. Thank you, Lee. All right, hang tight and look at Baji. I'm gonna go get my laptop, okay? Just 1 second. That's where the topic is. Because it's like my own thesis, right? Actually, I'm gonna make some tea too. I'm gonna make some tea as well. So, I'm gonna get the tea going. As well as the laptop. This is where the topic is. Oh, I'm tired. We will be doing this, okay? Hang tight. The tea is a-making. I'm making the tea as well. Yes. My phone text. Lee, are you still here? So Lee, I'm so sorry to hear about all the bad things during your sickness. Rudolph the Red-Nosed Reindeer. I'm back. I am back with the thesis. We're gonna talk about physics now. I'm better now. Oh, good. This is looking pretty good. I'm liking it. I'm liking it. I'm in my Christmas pajamas. Let me share the live. Can you guys share the live too? Oh no. Lee, can you share the live? It's okay, I'm better now. Good. Baji. He's so cute right now. Thank you, Lee. Marilyn says, yep. Lee says, sure. Thank you. Oh my you're here. We're going to talk about physics. So we're going to talk today about particle astrophysics, which is the topic of my own research and my own thesis. So it's a very close to my heart kind of topic, and we will be covering it. And the nice thing is that for this topic, of course, I just have my thesis and we don't need to worry about a book. Although I'm sure there are nice books on the topic as well, but we will mainly cover from my thesis. And I have been, when I talk about this particular topic, generally speaking, I end up sharing from my own experiences and certain adventurous stories as well. So I hope you're ready, and thank you for being here, and thank you for liking and subscribing, and thank you for sharing the live. I stopped the live for a second. Okay, well, I'm glad you're back. My tea is almost ready as well. Let me show you. Once this tea boils and I make my tea, I'm gonna sit down and put the blanket on, and then we'll talk about physics and my thesis. Hi, Fuji. Hi, Baji. Hi, Fuji. Hi, Baji. Ooh, let me also charge my phone while I'm over here. Tea is done. Do you play Call of Duty? It's a game where you can shoot. I've heard of Call of Duty, and I don't really play it. But I know it's very famous. Very popular, right? Am I right? Do you play Call of Duty? Yeti. Yes, Lee. Yeti. Oh, you know what? Maybe I'll do hot chocolate instead of tea. What do you guys think? Hot chocolate or tea? I'll do tea for now, and then I'll do hot chocolate as well. It'll be constantly drinking warm drinks. Constant warm drinks. I'm gonna make this tea. Ginger chai latte. Lee, do you know about this tea? Sachi, mama. Sachi. Their food is falling. Sachi. Here you go. Hikey! Hikey. Black tea maybe for flu better. Oh, Hikey. You're here. But ginger is also good for you, right? Oh. This is an S. Super sound. Fuji Baji. I cannot believe it. Okay. Snack time is done. I see you, Baji. Did you just do a fight? Okay. We're gonna sit down and read about particle astrophysics. I burned my tongue a little bit. Oh my God. They were grooming each other. Then they fought. I know, right? Fuji loves to take care of Baji. Baji always likes to get love from Fuji. Then they passed each other dramatically in the hallway. God, the boys are so dramatic. Look at this cool girl. The boys are so dramatic. Oh my God. Oh my god! Okay. Is everything good? Okay, I see. Good. Before I sit down, I really don't want... I want a little bit more charge on the phone. And then I want to sit down and start our topic and not be disturbed. Fuji, Suji, Baji, you're going to be good kitties throughout this life. Throughout. Okay. My tea thing is unplugged. Everything good here. Checking. 1, 2, 3. Testing. Breathing out, breathing in, off and off and off. Good. And off and off and up. Good. Breathing in and out. Once I sit down, babies, Mama is not going to be disturbed anymore. You've had your snacks. Putting a scarf on. I'm putting a scarf on. No more disturbances. Okay, is it still snowing? Hey Google, is it snowing right now?
Yes, right now in Malden there's a very high chance of snow.
Baji. Baji. Excusez-moi. Baji. Okay, it's 4:44. Great time to start this topic. So, we are live and we will be talking about physics now. We looked at the snow, we looked at the kitty cats, we even looked at some jewelry, and I'm here with my tea, and I've had a cold, but we will be now talking about particle astrophysics from my own thesis and work. I started this topic a couple of days ago, but I think there was a lot of coughing and whatnot, congestion in that particular live. So if you were present in that one, thank you for bearing with me. Today we will be talking about astrophysics happening far, far away. So, thankfully, this is going to be very exciting. Indeed. Indeed, very exciting. Let's see. Okay. Oh, I dropped everything. All the packaging from the jewelry I have dropped. Now, let's see. Let's see. I will be appearing in this myself. Let us see how this works. Now, usually, I do the other way, but I think I will be doing it this way now. Do you see me? Can you see me and hear me? I think you can. I see myself. Okay. Hello, hello. How are you? Lee and Dora and Marilyn and everybody. Hi, Key. Are you here? I'm still very bundled up. Actually, you know what? I kind of want to see I kind of want to do it this way. I think we'll just do it this way. Yeah, we'll just do it this way. So, we will be talking about, look at how bundled up. Look at how bundled up I am. We will be talking about my own topic of particle astrophysics today. So we have been covering modern physics, 20th century physics, special relativity, quantum mechanics. We then moved on to more recent physics, dark energy, dark matter, cosmology. We have spent quite a bit of time on cosmology, actually. And I think it's time that we talk about particle astrophysics, which is in the cross section of particle physics, astrophysics, and astronomy. And specifically today, the topic that we will see is actually about neutrino astronomy. So, astronomy traditionally has been done with visible light. When you look up at the night sky and you see the stars and galaxies and planets and things like that, when you look at the sun, don't look at the sun for too long, or the moon. Actually, don't look at the moon for too long either, because it is soft. Kitty as flu recovery. Okay, it is the sun's light that's getting reflected off of the moon. But traditionally, astrophysics and astronomy, especially astronomy as an observational science, has been done with visible light, which is just the light that you can see with your naked eye. Which is in the visible spectrum, because light has a spectrum of various wavelengths and frequencies, and you can have light with very big wavelength, also known as radio waves, and you can have light of very small wavelength, which is can be something like gamma rays. So if light has very small wavelength, such as, for example, gamma rays, then pretty much that light acts like a particle, like photons, because light has both wave and particle nature, dual nature of light. Even everything has a wave and particle nature, but the wavelength of something might be very large or small depending on which thing we're talking about. In the case of light in the form of gamma rays, these are light particles pretty much because their wavelengths are very small. So today we will talk about neutrino astronomy. In other words, this is astronomy or astrophysics that's done with particles other than light. And particularly when people talk about particle astrophysics, what they might mean is not just particles other than light, but really particles other than visible light. So particles that are not in the visible spectrum of light. So it could even encompass gamma rays or X-rays or something else. Let me think of another type of light. I think pretty much gamma rays and X-rays are, I'm going to just say those examples because those have smaller wavelength than visible light. And then we'll move on to some other examples of particle astrophysics, which will involve particles really, really other than light. So, because the ones I just mentioned, gamma rays and X-rays, are still a form of light. But you can actually even do astrophysics with other cosmic messengers, such as cosmic rays. These are pretty much charged particles that are made in various nuclear reactions or other types of sort of particle physics interactions in space. They're space particles. They might have a charge, and when they come into our atmosphere, in the Earth's atmosphere, when they hit the Earth, basically they can create an air shower or something like that, some sort of signature, and we can pick up on them as well. And they might be coming from a very far, far away extragalactic source or astrophysical phenomena. They can also be coming from interactions with the cosmic microwave background, which we have actually talked about in cosmology recently, in our cosmology topics recently. Let me just look at my notes as well. Yes, we talked about some cosmology topics recently where we covered the cosmic microwave background. We covered things like the early universe, the cosmic microwave background, this leftover radiation from when the universe was only 300,000 years old. So those are photons, and they can also interact with some particle and make another interaction, and some signature of that could be something that we also pick up on. So that would be something like a cosmic ray. The other thing is neutrinos. So we saw that neutrinos are an ingredient of the universe. They're in fact one of the 5 ingredients of the universe that we talked about, and they're also a fundamental particle. They're a type of lepton. So we also talked a little bit about particle physics. Let me just remind you that there are 3 main families of particle physics or particles, and these are leptons, quarks, and bosons. A lepton example would be something like an electron and also something like a neutrino. A neutrino is a tiny little particle with very low mass. They were in fact considered to be a candidate for dark matter. Another concept that we have also mentioned on these live streams. But turns out that neutrinos are very low mass, so they're not thought to really be the explanation of most of the dark matter, for example, in our own galaxy and other places. So we think that the question of dark matter is still open. We don't really know what dark matter is. But neutrinos are a fundamental particle. They are in fact made in a lot of different particle physics interactions and nuclear reactions. They are made in our sun. They were part of the picture in the very early universe. We saw some discussions. We had some discussions about the very, very early universe, which was radiation dominated. There were a lot of photons. The photons were the king of the jungle. They were constantly hitting everything around them and not letting things kind of stabilize and form, such as neutral atoms were not really a thing back when the universe was just kind of getting started after the Big Bang. It was too hot, too dense, too much going on, and anytime someone felt a little bit stable, like a little electron or a nucleus or something, a proton or something, it would get hit with a photon and it would again become unstable. So we kind of saw that in the Big Bang nucleosynthesis discussion that we basically could not really get anything beyond helium. In the early universe, we made hydrogen, we made helium, and that was about it. And we talked about some of the isotopes of hydrogen and helium and the reasons for why we made those things and how those were stable and other things were not. But in that particular picture too, we mentioned neutrinos. So neutrinos are a very important part of the universe, a very important part of pretty much any nuclear picture, and it's going to be an important part of today's discussion because we've been trying to use neutrinos as a way of doing astronomy as well. It's an alternative particle that we may also want to use to study the astronomy, to study the universe, especially because neutrinos are a fundamental type of particle. First of all, they're not a composite particle. For example, a proton or a neutron within the nucleus of these elements that we know. For example, hydrogen is an atom that is made up of a proton and an electron. Its nucleus is mainly just one proton. Depending on if you're talking about hydrogen versus its isotopes, hydrogen is going to be mainly just the one proton. But this one proton is not a fundamental particle in the sense that it breaks down further into quarks. So that's the second family of particles that I mentioned a little while ago. Actually, I said that there were leptons, quarks, and bosons. A lepton example was something like an electron or something like a neutrino. A quark example is something like an up quark or a down quark, which makes up, for example, the proton or a neutron within the nucleus of an atom. And then the last type of particle family was the boson. And an example of a boson is a photon. Okay, so a photon is what makes up light. It's a boson. Now, there can be other types of bosons too. I'm just mentioning some examples here. I'm not exhaustively covering all of the particle families and particle physics. But this is the standard model of particle physics that consists of leptons, quarks, and bosons. Some other examples of bosons would be the W and Z bosons, which basically facilitate the interactions between neutrinos. So neutrinos interact through something called the weak force. So there's gravitation. When it comes to forces, basically there is the electromagnetic force, gravitation, the weak force, and the strong force. So certain particles, basically, most particles will interact through more than one way. Like, for example, photons are the mediator of the electromagnetic force or electromagnetism. Light is what is it's the wave, it's the electromagnetic wave. Electrons can interact with photons. Electrons can also interact in other ways. But neutrinos, this is a particle that only pretty much interacts with the weak force. It does not also interact with electromagnetism, for example. So electrons have a charge, right? Neutrinos don't have a charge. They're chargeless. They're neutral. They do not interact through the electromagnetic force. They have some mass, so they interact with gravitation, but that mass is very small. For a while there, people thought that they might even be massless, which is not true, because pretty much the only particle that we think is massless is the photon, which is light. And light travels at the speed of light. We talked also about how important that is. The fact that light travels at the speed of light, and the speed of light is a constant of nature, where everybody traveling at whatever speeds in whatever frames of reference would still experience the speed of light as a constant. So even neutrinos think that the speed of light is the speed of light. It's a constant. A neutrino could be going at a very high speed, 0.5 c or something, where c is the speed of light constant. And even the neutrino would see the speed of light as the speed of light. It would not be seeing that the speed of light is 0.5 c if it itself was going at 0.5 c, something like that, you know. So this gives birth to special theory of relativity, and from there we can also go to general theory of relativity. We also talked about that in these live streams. I'm kind of giving you a lightning speed summary here. So in other words, neutrinos are very low mass. They don't have a charge. They only interact through the weak force, through the W and Z bosons. We don't have to talk about the W and Z bosons in a lot of detail right now. Astrophysics is science that employs the methods and principles of physics and chemistry in study of astronomical objects and phenomena. Hello, brilliant, lovely woman. Hi, crazy sick wine. How are you? Hello, hello, hello. So basically, why I'm talking about neutrinos right now is because this is the particle of interest for this particular topic that we'll get into. And also I wanted to familiarize you guys with the fact that astronomy is not done just with visible light. It is done with gamma rays, X-rays, cosmic rays, neutrinos, and even gravitational waves at this point, because we have even started to observe and measure gravitational waves. When there is a merger between a neutron star and a neutron star, or a black hole and a black hole, or a black hole and a neutron star far, far away, we have set up experiments now that can measure the gravitational waves from such mergers and explosive events. These same gravitational waves were predicted by Einstein in his general theory of relativity over 100 years ago. So when we measure them today, and we started measuring them pretty much in the last less than a decade or so, it's a very big deal. We didn't used to be able to measure gravitational waves from things colliding. And by things, I mean black holes and neutron stars. Like, oftentimes a neutron star is in a binary with another neutron star, or a black hole might be revolving around another black hole or a neutron star. And ultimately, so we talked about how when things are revolving around each other and there is a gravitational wave, basically they're releasing gravitational waves. They're ridding themselves of this energy. As they do so, they actually get closer and closer together while they do this dance, because these massive things that are putting massive dents into space-time, they're losing gravitational energy with time, and ultimately they actually get closer and closer, and ultimately they actually merge and they collapse into each other, and they collide and collapse together and create and give off even more gravitational energy, which come to us on Earth sometimes as gravitational waves that we expected to pick up based on general relativity. And nowadays, we can actually do this. We do have experiments and measurement devices in place to be able to measure these types of things, which we weren't used to be able to do over 10 years ago. This is a very recent thing. So even though we might have been designing such gravitational observatories for a while, the fact that we can pick up on these things now is a new thing. So this is yet another arm of astrophysics. So I wanted to mention that now in our list of cosmic messengers, we really have a number of items. We have photons, we can use them the old-fashioned way, visible light, visible light, gamma rays, X-rays. We have observatories that are sensitive to various parts of the spectrum. I'm 28. Is it too late to study physics? Of course not. Physics is a lifelong journey. It's definitely not too late to study physics. 28 is a very young age. You're very young, especially compared to the universe, which is 14 billion years old. So you should consider yourself to be a baby, just a baby. So astronomy is no longer only done with visible light. If there is one thing you take away from this live today, it is that we do it with visible light, with other parts of the light spectrum, with cosmic rays, with neutrinos, with gravitational waves. Because just imagine, we know about neutron stars, black holes, these things. But when we can pick up something like gravitational waves from these things, that give us a further probe into these things that we did not have prior. So it's almost like when you are sensitive to different ways of studying astronomy and astrophysics, as in you build experiments that can be sensitive to different types of particles, whether that be light and its different parts of its spectrum, such as different wavelengths of light, whether it be other particles altogether like neutrinos or cosmic rays, whether it be gravitational waves, making yourself and building yourself an experiment with the help of others. Of course, these experiments are all collaborations at this point. Some collaborations are bigger than others, but they're gigantic collaborations usually. When you build yourself experiments that are sensitive to different ways of studying astronomy with different particles or different medium, because see, gravitational waves, we don't really have the particle that goes with gravitational waves. Sometimes we write down graviton, but we haven't really discovered that particle, if you will. Gravitation and the standard model of particle physics are not exactly unified. This is something that we also talked about, which is the grand unification theory, which did not come true, as in it was not fulfilled by Einstein, even though that was his dream. It's a bit of a sad status, but it's motivation for you and me to work on it. But basically, why I hesitated about gravitational waves and calling it the graviton is because we don't actually have a compelling, true unification between particle physics and gravitation. Indeed, between quantum mechanics, electromagnetism, and gravitation. These things would be nice to have been unification, but it's not done yet. So we can't really say graviton, but theoretically, gravitational waves is like picking up on something like a graviton, if you will. Basically, I'm saying that everything is probably has a wave and a particle nature, but until you discover the particle, you can't really say that you have. We haven't discovered the particle that is mediating gravitation, really, right? So we can't really say that we have. But we do pick up on gravitational waves, and so that's definitely a thing. And we do have neutrinos. That's definitely a thing. We have experimentally observed. So I'm talking now about experimentally what we have. We have photons, obviously. We have neutrinos. Those are experimentally observed, discovered, measured, especially from certain sources, are definitely a thing. Sun neutrinos are observed all the time. We even have astrophysical neutrinos now, so it's definitely a thing. Cosmic rays, again, a thing. We have astrophysical cosmic rays and cosmic rays, cosmogenic cosmic rays that are formed in a cosmogenic way. We'll get into it in my thesis, but basically cosmic rays can be made in an astrophysical way and in a cosmogenic way. We'll get into it. Again, we have that. Neutrinos, we have that. Gravitational waves, we have that. These are all things that we have experimentally observed. We're good. We need to continue to observe them and continue to use them as probes of this universe and as probes of astronomy and astrophysics. But we have these things, and these are all the different arms of astrophysics at this point. And you need to keep these in mind when you are thinking about probing astrophysics at a large distance, okay? Thank you. How long does it take to get a PhD? Mine was exactly 5 years. Many people take a lot longer in the US. In the US, it's indefinite. You could have a PhD, you could not. At the end of those years, probably if you spend a long time and doing things, and your advisor will eventually kick you out, hopefully with a PhD. But PhDs are not a set time in the US. In other countries, it might be different. So you should look up, if you're interested in other countries like Germany or the UK or France, exactly how their PhDs work. I think it's a little shorter in other countries, but in the US, it's the most indefinite, is what I've heard. My advisor, so I'll just say some examples. My PhD was 5 years. That's considered short in the US. My advisor's PhD was 7 or 8 years. Hers was a I think she went to Berkeley. I think Berkeley PhDs are kind of long. I have a friend also did astrophysics. Hers was 7 years too, I think. And she went to Caltech. I have another friend who did condensed matter physics, and his was 6 years. And these all include a master's. So, I mean, the PhD that you start after your bachelor's. So, those are the timelines. Okay, so with that summary in place, we will now talk about my thesis. So my thesis is called Studies in Particle Astrophysics, and I just gave you a bit of a, introduction into that. I think I'm in love with you. Thank you. I gave you a bit of an introduction into particle astrophysics because the main thing I wanted you to understand is that particle astrophysics is nothing strange or, weird. It's just astrophysics, but it's done with particles other than visible light. Okay? And it's always important, like PhDs are pretty specific, right? I have a subfield, a subtopic, a specialization, but that does not mean that you should only talk about your specialization. So I spent all this time talking about gamma rays, X-rays, cosmic rays, gravitational waves, even though those are not really my specialization. But in research, you are supposed to be very well-rounded and giving lots of credit to all of the other things that belong to your overall field. It's kind of like you start really broad You start really broad and you narrow down into your topic. As in, probably for the most part in your PhD or your research, doesn't have to be. So I talk about my PhD thesis, but that's not the only way to do research, right? You could do research without having a formal academic position. You could be working in a lab of some kind without pursuing a degree, right? So I'm just talking about my experience here, but there are people who do research that are not in an academic position. They might just be working in a lab or even in a university and not actually getting a degree, you know? So it's up to you. But basically in research, you start really broad. You learn about everything in that field, and then you also learn about everything in the subfield, and by learn, I mean it's kind of a literature review. Basically, when you learn about the field, it's a literature review, then the subfield literature review, then the subfield literature review, and then you get into the really narrow part, which is your work, your focus, your topic, and there you are producing the literature, because that literature does not exist yet. So you have to do the work and progress the field or the subfield, and that's basically what is expected in academic type of research or in any kind of research really, where you have now pushed the boundary of knowledge in that particular little focus and added new information. But you always start really broad and you do the literature review of the field and the subfield and the subfield. You know, that's why when I started this talk, I mentioned about all the different cosmic messengers and all these different things. Why? Because that's how you're supposed to start. You mention everybody and you acknowledge everybody and you give everyone credit or they get very mad. So partly it's also the ethics of it. You're ethically expected to give credit to everyone. And then you can talk about you. Appreciate the information. Is it 6 years after high school? It's more like 6 years after your bachelor's. So first you do high school, finish it. Then you do 4 years of college. You need a bachelor's degree, usually, to get into a PhD program. So it's more like 10 years after high school. Like I finished high school and then I was in school for 9 years to get my PhD, including the bachelor's. So it's like high school, then 4 years of college, and then I did 5 years of a PhD program, so 9 years. And the people who take 6 years, 7 years, it's +4 for the whole thing. And then generally people also do postdocs. My postdocs were more sort of in industry, where I applied my physics background in certain jobs that utilized the background, but the jobs weren't always academic in nature. Some people mention postdoctoral research. They call it postdoc if it is academic. If it's not purely academic, then even though it's a postdoctoral thing, you don't really call it a postdoc. So, okay, so far I still haven't really told you anything specific. That's because the general information is very important. So now we'll get started. Exciting No, first I will take some sips of my tea. Sorry. I need to clear my throat here. I'm looking at my screen here because that's where my thesis is. Whoops. So does that make sense? Crazy sick wine, what I just said about the PhD timeline? Oh my God. Ugh, yes, definitely. Oh God. With your mind, I'm surprised you're not a millionaire yet. Yes, definitely. Thanks. Okay, good. That's a great point. Academic research and making a lot of money don't always go hand in hand. Generally, academic research is not the highest paying type of position, and we're not really taught financial education in academic environments. So, for me, for example, getting into finance and understanding more about personal finance is something that I had to learn on my own much after my PhD was already done. So, it's really much more of a recent thing for me. And being a millionaire and having money and making your money work for you, that actually is a time thing, right? Compound interest, money grows over time. So the sooner you start, the better. So it has less to do with academic research orientedness and passion and intelligence, and more to do with financial education and time than anything else. And finance is not something that we're taught in school or college or grad school or PhD, right? So so that's one layer of it. The other layer of it is that to make a lot of money, you basically have to have a business, right? That probably sells a product, and then you might have to sell that business and you make a lot of money. And that's not really something I've done in a big way yet. So partly, I'm an idiot. That's why I'm not a millionaire yet. There's really no excuse. Everybody is an idiot in some way or shape. I tried to be more financially smart in the last few years, where I started to learn more about it, 3-4 years maybe now, when I've started to learn more about finance. But until then, I was financially stupido. The nice thing about liking astrophysics and astronomy and all this stuff, though, is that you don't necessarily have to be very useful in life. The whole point of astronomy, like if I really wanted to be super useful in life and do something that affects some material thing on Earth, then I would probably pick a different major. So there's also that. A lot of astronomers believe in being useless. We believe that our passion is enough. It will take us through life. We will have a lifelong love and hopefully money to live on. You know what I mean? But I do believe now, in this day and age, in this economy, it's important to be financially educated and invest and do something about money. Yeah, no. Please find the PayPal donation link if you want to donate to my cause. I mean it. It's Christmas, guys. Okay, now we will talk about astrophysics. Um, so much more interesting. So, exciting astrophysics happen far, far away. According to me, because this is my thesis, we live in a boring part of the universe. This allows life and the life sciences to thrive here. However, everything that is interesting in astrophysics takes place far, far away. For example, most gamma ray bursts take place about 1 gigaparsec away from us. That is over 3 billion light years away. For reference, our own galaxy is about 100,000 light years across. So this is your story. I have to remember it's biased. Yes. So our galaxy is approximately 100,000 light years across. It takes light 100,000 years to go from one end of our galaxy to the other. So imagine 3 billion light years. That's a very long distance. Hi Lee. Hi 1969. Narc YZ. Hello, how are you? 3 billion light years away. That's very far. So according to me, apparently, we live in a boring part of the universe. This allows life and the life sciences to thrive here. However, everything that is interesting in astrophysics, according to me, takes place far, far away. For example, most gamma ray bursts take place about 1 gigaparsec away from us. That is over 3 billion light years away. This is very biased. I think people would be mad if they, not everyone thinks that all of astrophysics happen very far away. But I guess I thought that. Why are gamma ray bursts interesting? Question mark. Well, in short, they are nature's most powerful accelerators, and they outshine an entire galaxy when they occur, with luminosity of around 10 to the 52 erg per second. What is more, the physics behind these exotic events continue to remain mysterious for over 50 years. 50. Wow. Traditional astrophysical messengers are not able to completely probe physics that take place at the farthest distances and at the highest energies. Since the beginning of astronomy, we have relied on optical light, or visible light, to study objects in the sky. In the last few decades, we have started utilizing light of other wavelengths, such as X-rays and gamma rays. However, light of energy 1 MeV and above can undergo pair production. Light of energy 13.6 eV gets absorbed by hydrogen atoms. The most abundant element in the universe is hydrogen, while light at other wavelengths gets absorbed by other atoms and molecules. Light is the astronomer's best friend, but there is an inevitable need for complementary messengers. Wow. Nicely written, past me. Fortunately, in the last century, we have opened up multiple new windows to peer into the universe. About 100 years ago, cosmic rays were discovered by Victor Hess in a balloon-based experiment. In the last several years, not decades, years, the Ice Cube Neutrino Observatory has discovered the first astrophysical neutrinos up to energies of a few PeV. That's 10 to the 15 eV. Moreover, gravitational waves were discovered by the LIGO collaboration in the last few years. I was mentioning, confirming, for example, the association of short gamma ray bursts with neutron star mergers, which is, by the way, a really big deal. Really, 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 really big deal. Because we did not have that confirmation. We thought that neutron star mergers are associated with, that short gamma ray bursts, because gamma ray bursts, we will see later on, come in a couple different categories, long gamma ray bursts and short gamma ray bursts. And we thought that short gamma ray bursts are associated, we think this must be associated with neutron star mergers, but we had not confirmed that until gravitational waves were measured for the first time. Yay. Neutrinos as astrophysical messengers. Neutrinos are potentially perfect candidates for carrying information about distant particle accelerators all the way to us. 1 second. I need to blow my nose. Sorry. Still recovering. Hello, everybody. Thank you for being here. One second. Need to go off camera. No need to see me blowing my nose here. Wait. Where is my... Feel free to like the live. I know. Gross, but being a human is Jesus. Thank you for your patience. I feel like I should okay. Done. We'll come back. So Lee said, I have to remember it's biased. Yeah. Yeah. Pretty much everything is biased. You have to do your own research. This is why independent opinion is good. Take into account everything that everybody else has done, but then also do your own research. Okay, neutrinos as astrophysical messengers. Neutrinos are potentially perfect candidates for carrying information about distant particle accelerators all the way to us. So these are nature's particle accelerators, natural particle accelerators. So this is my way of introducing neutrinos to you. Due to being neutral and weakly interacting, neutrinos would remain unattenuated and point straight back to their source. In this way, they would have a definite advantage over messengers such as cosmic rays. So I mentioned cosmic rays. Neutrinos are the side product of almost every nuclear reaction and can carry versatile information about particle physics taking place at cosmic distances. Their association with sources such as gamma ray bursts would confirm, for example, whether protons, in addition to electrons, get shock accelerated in the fireball model of the gamma ray burst. So I haven't given you a full introduction to gamma ray bursts yet, but I'm just kind of motivating what neutrinos would kind of help with as I introduce the topic here in my thesis. As I introduce pretty much neutrinos as a cosmic messenger, there are important consequences of observing neutrinos from specific sources in astrophysics, and that's what I'm talking about here. I believe that neutrinos from gamma ray bursts are still not really confirmed. So, and especially it wasn't confirmed during the writing of this thesis. So it was a big motivation. Despite a lack of observations so far, ultra high energy, which is greater than 10 to the 18 EV energy, neutrinos are predicted to be produced in two ways. The more commonly referenced of which is known as the cosmogenic method. So I mentioned that already. The cosmogenic method entails the interaction of cosmic rays with the cosmic microwave background. So the cosmic microwave background is a bunch of photons from the early universe, and guess what? Cosmic rays can interact with these photons and give us a cosmogenic source of neutrinos. So I'll show you that in a second. Ultra high energy cosmic rays are predicted to travel only about 50 megaparsecs before they interact with cosmic microwave background photons, a phenomenon known as the GZK effect. This is thought to cause the sharp drop in flux at the highest energies, as seen in, I'll show you. Such an interaction can also potentially lead to the production of ultra high energy neutrinos, although no cosmogenic neutrinos have been observed so far. The second way of producing ultra high energy neutrinos is the astrophysical method, which is the one I find to be more motivating. Me. The astrophysical method involves the production of ultra high energy neutrinos in nature's most powerful particle accelerators, such as gamma ray bursts. This will be discussed in more detail in Chapter 5. In both the cosmogenic and astrophysical methods of producing ultra high energy neutrinos, a commonly referenced process of production of the same is through the interaction of a proton and a photon, creating intermediate pions, as shown in figure 1.4. Okay, now we will look at these figures. So first of all, this is depiction of a gamma ray burst. This is a picture. The credit is NASA EPO, Sonoma State University. So sort of just a picture of a gamma ray burst. Then this is the different cosmic messengers: optical light, visible light that we have used traditionally to do astrophysics and astronomy; gamma rays, which is the light of smaller wavelength, and light that we see from things like gamma ray bursts; cosmic rays, these are the charged particles made in different processes and which can interact with the cosmic microwave background photons that I mentioned. But in general, these are just particles that could be coming from various sources and telling us about those sources. Neutrinos, that's the fundamental particle I've been also introducing here. It's a lepton, and it is made in various different processes as well. In fact, it's made in pretty much every nuclear reaction. So depending on which one, you could learn about astrophysics through neutrinos. And then lastly, gravitational waves. We get gravitational waves, especially from certain very big explosive phenomena like neutron-star merger can produce so much gravitational energy that we would pick up on it even on Earth, even though the event might be happening very far away. And this is also a way in which we could study astrophysics nowadays. So that's what that is. Astrophysical messengers. Pictures are all borrowed from Fermi, IceCube, and LIGO collaborations and the internet. Okay. And then here is the the cosmic microwave photon. This is the cosmic microwave background radiation picture. This is a very famous, very common picture of the cosmic microwave background radiation. And this is basically showing that the cosmic ray that's traveling through, say, space will come to meet the photons in the cosmic microwave background. Remember, there's these photons from the early universe, and cosmic rays, it doesn't matter where they are made. Say they're just traveling through space after being made somewhere else. As soon as they meet with a cosmic microwave background photon, and depending on its own energy, it can actually interact. And basically, the cross sections of these interactions are such that cosmic rays will not go too far. Basically, 50 megaparsecs is the limit of how far it would go before it meets with such a photon and goes through an interaction, and that gives us a dip in the flux of these cosmic rays. And that's what I talked about before. So here it is, depiction of a cosmic ray interacting with the cosmic microwave background, thanks to the Planck telescope for the CMB picture. So this is from Planck telescope, the picture. This bottom plot right here is the energy spectra of cosmic rays measured by different experiments. See, all these little points come from various different experiments that are listed over here. Auger, HIRES-2, Tunka, and Yakutsk. These are various places that they come from, and various journals in which these are basically published. And what this is saying is that this energy spectrum, see, basically we have energy is on the x-axis, and we have sort of a flux, let's say. This is a sort of a complicated term right here on the y-axis, but this is the how much of these, how much cosmic rays, sort of a notion for that, which is in the y-axis, a flux of cosmic rays. So energy spectra of cosmic rays measured by different experiments. So all these different experiments have measured, let's say, sort of a flux of cosmic rays as a function of its energy. And this is what we find. There's a certain shape to this plot. So Andreas Hongs showed this plot at the 13th International Conference on Topics in Astroparticle and Underground Physics. Ultra-high energy cosmic rays can only travel for about 50 megaparsecs before they interact with cosmic microwave photons and lose energy. Right here. And therefore, we see a sharply falling spectrum at about 10 to the 20 eV energy. So right here, this is what they were trying to explain. Why does the spectrum fall so sharply at a specific energy? And that's because the cosmic ray will meet with the photon and interact with that photon and lose energy in that process. So the ones that are coming to us is very unlikely to have energy above 10 to the 20 eV because it's already interacted with a cosmic microwave background photon by then. Excuse me. And we're not going to see cosmic rays above a certain energy because of that, because the likelihood, especially if it's a very high, see, higher the energy of the cosmic ray, too, more chance of it interacting and meeting with a photon or something like that, especially because the cosmic microwave background radiation exists as well, which gives you availability of these photons. Higher the chance that it will interact, and in that interaction, it will lose energy. So it's almost like nature prevents us from seeing particles or cosmic rays of higher energy than that, because the higher energy ones have already lost their energy by through these interactions. And it's a cosmogenic. We call this a cosmogenic interaction because it's not happening in a particular astrophysical source or something like that. The cosmic microwave background radiation is the photons from the early universe, from when the universe was around 300,000 years old, and you saw the how homogeneous it looks, right? Like that's the smooth universe we've talked about in cosmology. So we will come back to this cosmic microwave background radiation picture again and again. Good thing you saw it here in my thesis, but it's something that comes up a lot in conversations of cosmology, especially because that's the smooth universe, the homogeneous universe in the early days. And that type of photon just hanging out means that the cosmic rays, especially the really high energy ones, they're gonna interact with such photons and lose energy, and we're not gonna be able to see. Even though these cosmic rays are probably extragalactic, they're coming from far, far away. They could be coming from some very exciting phenomena that we would have loved to learn about, and we do learn about, and we do see them to an extent, but there is a limit to where we can't see them beyond a certain energy at a high level. Basically, that diagram I just showed you with the sort of a flux in the y-axis and the energy in the x-axis is what we call the spectrum, right? That's the cosmic ray spectrum, as in how much cosmic ray are you seeing at what energies, right? The lesser energy, lesser EV, because let's just let me look at it without showing it to you. Say like 10 to the 15 EV or so cosmic rays, we see a lot of them, right? The flux for cosmic rays at around 10 to the 15, 10 to the 14, 10 to the 16, 10 to the 17 EV is a lot, you know? So, okay, so those ones we see a lot. But then you see that they're kind of decreasing, and then there's a sharp drop at like 10 to the 20 EV. And that all has to do with this understanding of, well, cosmic rays are pretty extroverted. They will interact easily with things and with photons especially. And as soon as they do that interaction, they're going to lose their energy. And so those high energy ones, which are going to be extra looking for interaction, will have lost their energy already before we see it. So we have a limit of what by the time they're coming to Earth, they've already lost their energy, and we're not going to be able to see those high energy ones at a very high rate or a very high flux. We will see them much less. They're going to be much more rare. Okay, so that's that's about cosmic rays. The plot you just saw and this cosmogenic discussion that we just had is about cosmic rays, because you know, particle astrophysics is done with all these different types of things now, right? Cosmic rays is an important arm of particle astrophysics, and we must understand them to a certain extent, even though they might not be our focus. Like my focus was neutrinos, but it's always important to understand everything else that's going on in the field as well, because otherwise it doesn't make sense. Your research has to kind of, it's part of the bigger picture, right? And cosmic rays are definitely part of the bigger picture. There are people who only do cosmic rays, so you have to consider them in the story. And that's what this is about. Especially something like this plot that I showed you is a very standard, very well understood, well talked about kind of plot, okay? So that was the GZK effect plot. Now we will talk about the next part. So the second way, so that's the cosmogenic way. We will actually come back and talk about it some more in a little bit of time. Oh, you know what? Let me show it to you right now. Let me reread this part. So, despite a lack of observation so far, ultra high energy, ultra high energy, that term is given to particles that have energy over 10 to the 18 eV. So, ultra high energy neutrinos are predicted to be produced in two ways, the more commonly referenced of which is known as the cosmogenic method. The cosmogenic method entails the interaction of cosmic rays with the cosmic microwave background, photons, as depicted in the thing I just showed you. Ultra high energy cosmic rays are predicted to travel only about 50 megaparsecs before they interact with CMB photons, a phenomenon known as the GZK effect. This is thought to cause the sharp drop in flux at the highest energies as seen in figure 1.3b, which I showed you with the spectrum falling. Such an interaction can also potentially lead to the production of ultra-high energy neutrinos, although no cosmogenic neutrinos have been observed so far. Now, let me show you this interaction. So, I told you how cosmic rays will interact with the cosmic microwave background photons. So it's an interaction between a particle and a photon, which make the cosmic rays lose energy, and we don't see too many of them above 10 to the 20 eV. But now let me show you how this same story will actually also produce neutrinos as a side product. So it's a potential ultra high energy neutrino source as well. And this is how that's done. So this is a little bit of particle physics, but basically this is a proton. Let me just use this as a pointer. So a proton and a photon, because sort of basically in terms of particle astrophysics, a cosmic ray is a charged particle, right? That's made in some astrophysical or whatever process. Well, an example of a cosmic ray is a proton, simply the, because we know that the most abundant element in the universe is the hydrogen. And a proton is basically a hydrogen nucleus. So if the most abundant element in the universe is a hydrogen, then this interaction is probably going to be pretty common because there's a ton of just protons hanging out or being formed. And there's also the cosmic microwave background radiation, which is basically photons or light. So a proton meeting with a photon and interacting is a very common or pretty well understood type of interaction. So it makes an intermediate particle here called the delta plus, which has this energy, which can then go on to make, so the delta plus is very unstable, so it makes a neutron plus a pion, or it can make a proton plus a neutral pion, another type of pion. Now, if it makes the positively charged pion, then that positively charged pion, which is also an unstable particle, can make a muon plus a muon neutrino, which can then make a positron and an electron neutrino, a muon antineutrino, and a muon neutrino. And then if it had made a neutral pion, you would get gamma rays out of that. And if it had made a neutron, you would get the proton, electron, and antineutrino here. So all in all, from this particular type of interaction, like because of this proton and photon interacting and making the delta plus, which is an unstable particle, after all this happens, you basically get potential ultra high energy neutrinos. So I had mentioned at one point that neutrinos are made in most nuclear type of reactions. Most things that interact in particle physics, basically, this was just a proton and a photon interacting, right? But the problem is that when a photon and a proton interact, they can make these unstable type of intermediate particles that don't
that don't basically hang out for long. They have to, as they lose energy, they basically break down into more stable and fundamental particles, and the neutrino is a fundamental particle. It's almost like you got really excited, you met with another thing, you made some interaction happen, and you made an unstable particle. But the point is that that unstable thing isn't gonna be the final state. That unstable thing will then break down further into more stable particles and more fundamental particles. And neutrinos are a fundamental stable particle. They don't break down further into even smaller particles, at least not so far that we know of. So pretty much the long story short is that the proton and the photon, or a cosmic ray and a photon, interacting together, making something like the delta plus, making some intermediate pions, will ultimately lead to neutrinos, is the thought behind the particle physics of this. So we expect that we know that there are cosmic rays that are zipping across the universe. They get made in something, they come out of something, then they meet with a cosmic microwave background photon, because that's a thing too. And we expect that they will make this intermediate type of unstable particle like the delta plus, the pions, and ultimately they will break down into something like the positron, which is the electron's anti-particle, and some neutrinos, whether that be muon neutrinos or electron neutrinos. Because, by the way, the neutrino has 3 different flavors. So it's a detail for now, but basically this is the method by which, basically, if you made a pion plus, then that would, depending on the pion you're making, which is an intermediate particle, so you might not have heard of the pion too much because it's not a stable particle. So if you made a pion plus, which is a positively charged pion, then it will break down to more stable states of the muon plus, the muon neutrino, and the muon plus, the muon particle is also a lepton. The muon plus can then break down into the positron, and the total thing can break down into the positron plus the electron neutrino plus the muon neutrino's antiparticle plus a muon neutrino. But all in all, you're getting 3 different neutrinos there. And if you made a pion 0, as in a neutral pion, good job, that will also still break down into photons, into gamma rays. Because a pion is not very stable. Ultimately, it'll break down into something more stable, whether that be muon and neutrinos or the gamma rays. And then even if you made a neutron, if it has this unstable energy, even a neutron can decay into basically a proton and the electron and a neutrino. So for example, even in the simple case of a neutron decaying, it will not decay into just the proton and an electron, because a neutron is neutrally charged, right? So when it decays, it can make a proton and an electron, but it won't just make that. It will also make a neutrino. Okay, so in other words, the neutrino, whether it's an electron neutrino, a muon neutrino, or a tau neutrino, there are 3 types. Neutrinos are very commonly made in a bunch of different interactions. It's almost like the neutrino is basically this side product, this particle that kind of chills, and other things will decay into it because it's a stable fundamental particle. So even if you made a pion, if it's a charged pion, you'll probably get neutrinos at the end. If it's a neutral pion, you'll get photons. And that photon can, by the way, go and excite something else, and then through that interaction, ultimately, again, you get neutrinos. So neutrinos are the side product of many, many different interactions. They're fundamental and they're stable and they're weakly interacting. So they don't go and interact much more. And so we expect that if we build good detectors for neutrinos, and we'll get into what that means, good detectors, right? Because that's going to be a whole challenge. We expect that we should be able to pick up on signatures of these neutrinos because they don't interact much. So once they're formed in these various types of reactions and interactions happening between when they were made to when they come to Earth, we expect that they would not have interacted much more along the way because they are stable and fundamental and they're weakly interacting. They only interact through the weak forces and through the W and Z bosons. They don't interact with electromagnetism. They don't interact with the strong force. They don't have much mass. They're not charged, so they're not going to get deflected by, say, magnetic fields in a galaxy or something like that. So we expect that they should come straight to us after they're made, and they should point straight back to where they came from. So it's almost like light coming from a source, but not really light. It's a neutrino, and it should point straight back to its source. So that's the whole point of the neutrinos. We expect that they will be stable and good messengers of astrophysics, but they can be incredibly difficult to measure depending on the energy of the neutrino and so on and so forth. So we'll get into the challenges part as well, but this is the whole story of why the neutrino is also considered a messenger and sort of an example of how they're made. Okay. So real quick, before I pause, I will just finish up the rest of this part. We will talk about a couple different ways in which neutrinos can be detected. So one way is optical Cherenkov neutrino detectors. So now that we've established that neutrino is a cosmic messenger and potentially they're made in these types of interactions, we just have to detect them now, right? For that, we have to build very special, specific detectors for neutrinos and deal with the challenges of neutrinos. The same things that kind of make the neutrinos difficult to detect are actually why the neutrinos would be potentially a good messenger, because if they don't interact much with most things, then they're more pure messengers. They should point straight back to their sources instead of being deflected and losing energy and things like that along the way. So there's a big reward potentially of detecting these neutrinos. That's why we work on them. So one way to detect them is the optical Cherenkov neutrino detector. Optical Cherenkov neutrino experiments look for high energy neutrinos in the energy regime of 10 to the 11 to 10 to the 15 eV. So they're not as high as ultra high energy neutrinos, but they're still pretty high energy. In this section, we briefly introduce two optical Cherenkov experiments, IceCube and Antares. Being located in complementary hemispheres of the Earth, these two experiments have complementary fields of view. Where they are on the energy scale as compared to other particle physics experiments is shown in figure 1.5. I'll show you. IceCube is the optical Cherenkov detector in the southern hemisphere. The observatory is located in the South Pole. So literally at the South Pole, because you know Antarctica is a continent. Antarctica is bigger than Europe as far as the size of the continent goes. Pretty sure. So Antarctica is not just a small place, right? It's a continent. So when I say there are experiments in Antarctica for these types of things, it doesn't mean that there's only one spot in Antarctica where we go for these experiments. So the South Pole is just one part of Antarctica, and turns out IceCube is actually at the South Pole. Like there's a base called South Pole Station. That's the one we've built to support the logistics and the operations of IceCube, which is the name of this particular neutrino detector that I'll be talking about in just a second here. But basically, the South Pole is only a part of Antarctica. Antarctica as a whole is more than the South Pole. But if you wanted to work on IceCube, then you would actually go to the actual South Pole, which, by the way, fun fact, is very high altitude. So you might get altitude sickness, and people have to be very fit and very healthy to go to the South Pole Station, and you might be a little sick. So if you go there, just kind of take it slow. Take it slow, and don't try to do too much too quickly. Okay? Just a fun fact. IceCube is the optical Cherenkov detector in the southern hemisphere. The observatory is located in the South Pole. The completed IceCube observatory is composed of 5,160 digital optical modules called DOMs, digital optical modules, each containing a 10-inch photomultiplier tube with 60 DOMs placed at depths between 1450 and 2450 meters on each of 86 vertical strings. So 60 DOMs are placed at depths between 1450 and 2450 meters in the ice on each of 86 vertical strings. So we call this instrumenting the ice, by the way. And we literally instrument the ice thickly with these photomultiplier tubes in the case of IceCube. I'm just talking about IceCube now. The total instrumented volume of IceCube is 1 cubic kilometer. So it's called IceCube because it's literally a cubic kilometer of ice. IceCube, cubic kilometer of ice that we've instrumented with photomultiplier tubes to search for cosmogenic and astrophysical neutrinos. So that is IceCube in short, okay? It's a very expensive, the most famous neutrino detector. And it's actually at the South Pole of Antarctica, okay? Another complementary experiment that I wanted to mention to you for neutrinos, which is in the northern hemisphere. So IceCube obviously instruments the southern hemisphere and the southern sky. The neutrinos that will be coming towards IceCube are going to be from the southern sky, and also the ones that are going through the Earth from the other direction as well. But many of those will probably be sources of noise for IceCube, but those are not to be forgotten, okay? Neutrinos can go actually through the Earth as well, right? Very easily. So, but the cool thing is that IceCube, being at the South Pole, sees the southern sky without too much trouble. There's still going to be trouble in the sense of there's still going to be noise, but the southern hemisphere is very underrated. There's much less people in the southern hemisphere causing anthropogenic noise and such, but there's still going to be a lot of problems in the southern sky as well. But still, it's kind of cool when most of us are in the northern hemisphere, so we see the northern sky. IceCube sees the southern sky. Good, great. Antares is in the northern hemisphere. This is a complementary neutrino detector which we have placed in the Mediterranean Sea. So if you go to the Mediterranean Sea, you might just meet with Antares. Located at a depth of 2.4 kilometers in the sea, it consists of 12 vertical strings separated from each other by a typical distance of 70 meters. So we're instrumenting the sea now with only 12 vertical strings. So it's not as big of a deal as IceCube, let me just say. But Antares people, don't come at me. I mean, you can if you want. Each string is anchored to the seabed and held upright by a buoy. By a buoy at the top. Over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes. Wow. Over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes building a three-dimensional array of 885 PMTs in total. The instrument volume of ice cube of Antares, the instrument volume of Antares is 0.02 kilometers cubed. So it is not as big as ice cube, which is fine. It's a complementary experiment. Not every experiment is going to be the same and, identical as other ones, right? It's still important. Even if your effort is smaller, it's still important because it's important to get data from multiple sources and multiple ways and multiple types of detectors. And Antares is in the northern hemisphere, so it sees the northern sky. It will have other types of noise, other types of problems, and it's very, very good to have multiple types of detectors and multiple types of people working on these multiple types of detectors so that you're bias free as much as possible, and you also get information from multiple different sources. So even though Antares is a smaller effort, it's still very important. Complementing IceCube is very important. IceCube and Antares are both optimized for the detection of muons from charged current interactions of high energy astrophysical neutrinos. So basically they're looking for the muons that will be formed when high energy astrophysical neutrinos interact with the medium and make the secondary particle, which is the muon. So this thesis is a particle astrophysics thesis, right? So it will be very common that particle physics stuff will come up. Even though our motivation here is astrophysics and understanding astrophysics, you have to understand that the way we're going about it is through particle physics. So if you like particle physics, this is going to be a lot of fun. But if you're thinking that, oh my God, I don't care about particle physics, I am going to just warn you now that there's going to be particle physics coming up randomly all the time, because our detection method is not traditional astronomy, right? Our detection method is particles, and we want to see a specific particle, and there is a plan for that, and there is generally a particular signature or a particular interaction we're trying to capture or detect or measure on. And oftentimes particle physics is like a jungle of particles, right? It can be a little confusing. Like you might be like, what are you talking about? Why do you care about muons? It's because the neutrino, it's just this small particle. It's going to interact with the there was a noise. When it hits the earth, it's not going to give us a lot of time and write us a letter about, hey, I've hit the earth, can you measure me? It's going to be very fast, and it's going to quickly turn into other things when it does hit us, when it does hit the earth, whether that's the Mediterranean Sea in Antares or the ice in IceCube. And we have to be ready to pick up on the interaction that it does in the medium. So you'll notice that a lot of these neutrino detectors, the detection medium is something like ice or water or salt or whatever. And we want to instrument the detection medium because as soon as the neutrino interacts, it does something. The something will be different for different experiments, but whatever that something is, we want to detect it and be ready with our instrument to pick up on that particular signature. And in the case of these optical detectors like IceCube and Antares, they're both optimized for the detection of muons. Muon is another type of lepton. It's also part of the lepton family. And it's a secondary particle that is made from what we call charged current interactions of high energy astrophysical neutrinos. I'll show you the interaction in just a second here. But IceCube uses the Antarctic ice as a target medium for high energy neutrinos to interact in. And Antares uses the seawater instead. They both look for optical Cherenkov signatures of high energy neutrino interactions optical Cherenkov signatures. We will get into it, but that's what we're looking for with IceCube and Antares, of these high energy neutrino interactions. Because remember, these neutrinos are not the neutrinos from the sun. They're not low energy or medium energy neutrinos. These are high energy neutrinos. Depending on the energy of the neutrino that you're trying to detect, basically this will be very important. Depending on the source of neutrino that you're trying to go after. Like for example, the neutrinos from the sun, they're made in the sun, their process, their story is different. But if you're trying to go after detecting a neutrino from, say, an extragalactic, exotic, big explosion, big phenomena type of event, then that neutrino is expected to have more energy, okay? And you can say that neutrinos that are lower energy, I don't even care. I don't need to make an instrument or a detector that is sensitive to neutrinos that are any lower energy than some limit of the energy, some lower limit of the energy. And you can just say, you know what, if the neutrino has an energy below 10 to the 11 EV, I don't care. I don't care. So I'm going to make my detector based on that. So the energy is going to be very important. Yes, secondary particles. So basically, they both IceCube and Antares, they're instrumenting a certain detection medium. In the case of IceCube, it's ice, Antarctic ice at the South Pole. In the case of Antares, it is the Mediterranean Sea or seawater. But in both cases, they're looking for high energy neutrinos. Not low energy, not medium energy, not ultra high energy, but high energy, which is generally speaking considered to be between, actually we'll see exactly what they're sensitive to in just a second here. But Antares is sensitive to neutrinos of energy 10 GeV. So a GeV is 10 to the 9 EV, right? It's a giga electron volt. 10 GeV is like 10 to the 10, whatever. So Antares is sensitive between 10 GeV and 100 TeV. TeV is 10 to the 12. IceCube was built to detect neutrinos of around energy 100 GeV and higher. So IceCube wants to detect neutrinos of energy at least 100 GeV and higher. So that's 10 to the 11 EV. 10 to the 9 is GeV. 10 to the 11 is going to be 100 GeV and higher. So IceCube is basically saying, if the neutrino is under 100 GeV, I don't give a shoot. I want it to be at least 100 GeV and above, because those neutrinos have a more interesting story. They have an astrophysical source. They have a certain astrophysical aspect to them or a angle to them that I give any shits about. And if you're below that, then you're made in some other source, and I don't care. Thank you. That's what IceCube is saying. However, as shown in IceCube, as shown in whatever. So this is what IceCube intended, but turns out IceCube can also detect neutrinos that are slightly lower energy. So, because sometimes experiments are built for a certain thing, and they can be, surprise, sensitive to other things. Because human beings are not perfect. When we design experiments, sometimes it can be a lucky mistake, or it can be an unlucky mistake. But we go for a thing, something else can happen, So it's okay. IceCube is overall a great detector. Antares, all of these experiments we'll talk about, they all are great efforts, okay? But IceCube can sometimes see lower energy neutrinos. It probably drives the grad students crazy, but they do have some lower energy stuff as well. But you know, that's fine. You could have a whole other type of physics that you are now sensitive to just because you see the other stuff. You know, sometimes it really is a lucky mistake, okay? So let me show you something here to show you what it is I'm talking about with these energies. So I mentioned above how it's very important to start broadly speaking, the field, then you narrow down, then you narrow down, then you narrow down, then you narrow down, subtopic, right? With this energy stuff too, it's very important to be broad and appreciate all of the regimes of energy in which experiments are done and what those regimes give us in terms of neutrinos, their energies, their sources, and the type of detector that you can build accordingly, and the type of physics you would be probing accordingly, and also to mention all your friends and enemies. Hopefully just friends. Because everybody else who's working in the field are all your collaborators and friends and colleagues, and their work is important too. So when you start about talking about your own work, first talk about everyone else. Otherwise, they will feel like you forgot them, and they will tell you that you know nothing because you didn't mention them. So don't make that mistake. Hi, Yashua. Jew or Christian? I have to ask if the neutrino is a Jewish or Christian. I don't know. I don't know if the neutrino has a religion. Are you Sashu of Yahweh? I don't know what that is. Sorry. Neutrinos are very introverted. I don't know if they're Jewish though. Maybe. Okay. Let me show you something. And after that, I need to take a lot of sips of my tea because enough is enough. This is my favorite topic, guys. So I'm talking way too much and I'm still sick. And, oh shoot, I only have 4% charge on my phone. So after we look at this diagram, I will charge my phone as well and get back to the topic here. So look at this. This big black arrow that I drew for you guys here for my thesis is giving you the energy scale in a cartoony kind of way. So on the left here is basically the energy scale starting at less than 10 to the 9 EV or a GeV. In the middle, we have 10 to the 9 to 10 to the 17 EVs range. So it's a broad range. And then on the right here, we have energies of above 10 to the 17 EV. And along with this black arrow, you're seeing all the different experiments and the different regimes of energy and work and experiments that we can do for neutrinos. So on the left, the experiments that are interested in neutrinos that are lower energy, something like less than 10 to the 9 EV or a GeV of energy, are experiments like DUNE and Hyper-K. Some of you might be familiar with DUNE and Hyper-K. Hyper-K, I believe, is in Japan. So they are interested in completely different types of neutrinos. Those neutrinos are from other sources and probing other types of physics. And those are those experiments. In the middle, we have the high energy regime. This is experiments like what I mentioned just now, Antares and IceCube. And you can see also LHC, the Large Hadron Collider, is also part of this regime where the center of momentum energies of the particles are going to be less than or equal to around 14 TeV. And Antares and IceCube operate around a TeV. The more specific ranges I mentioned just a moment ago. So that's that. Then we have something like Askarian radio array or ARA and Ariana. These are also neutrino experiments that kind of straddle both these regimes. They're kind of in between high energy and ultra high energy regimes. So we will mention both Askarian radio array, ARA, and Ariana. And then squarely in the ultra high energy regime, So the super high energy regime type of stuff, where the center of momentum energy of particles involved would be greater than 45 TeV, are things like ANITA, Auger, and New Moon. ANITA is the experiment I worked on, and we will get into that. But see how this is the big picture of the different energy regimes. The ANITA experiment looks for particles, specifically neutrinos, of energies that are close to the extreme right of this energy scale. But showing you this, I'm kind of telling you about the energy regimes and the other experiments that are part of this field, because that's, again, very important. You don't want to just do your own work and ignore everybody else. You want to talk about everybody and then talk about where your work fits into the bigger picture. And that's why I show you this big picture. And my focus was really just mainly this ANITA experiment right here. But I learned about all of them because that's what you have to do. Okay, now I will be charging my phone and sipping some more tea, and we will get back to this discussion. Okay, so thank you so much for being here and welcome to the live. And also, if you have any questions, now would be a great time to ask them. And I will look at your comments and questions and do shout outs and charging my phone all at the same time, okay? Give me 1 second. Any questions? I am not Jewish as far as I know, or Christian. I was born a Hindu, so that's what I am. Any other questions? Oh my God. Oh my God. I think to be Jewish, you have to be born Jewish too, right? I'm not an expert on religion, unfortunately. So I don't really know too much on this topic. I know the religion of neutrinos is to not talk to too many people. Good God. All right, I'm charging my phone. It's at 1%. And I'll let you also look at my laptop screen, actually, because this last picture I showed you is a very important one. This is, it's important to understand the energy regimes. So indeed, look at them carefully. Oh my God. Okay, I don't want to make my laptop do something weird here. There. Oh, this live doesn't let me rotate my phone, so I'm kind of stuck like this. I will find a way. I always do. I'm trying to charge my phone as well as show you the screen here. There. Let's do that. Ooh, look at that. Modern technology. There. See? There. Okay, so yeah, we just covered the energy regimes that we're going to get into, okay, or the energy regime of this topic. And because when we talk about particle astrophysics, it's extremely important to understand that particle astrophysics is sensitive to various energy scales. the astrophysics that you probe is different at different energy scales, and the detection method that you employ is also different for different energy scales and regimes. So you really have to pick sort of kind of where you want to be. Not that you have to be super specific, because you could basically operate in a range of energies, as do many of these experiments. But this is to show you, broadly speaking, where all the experiments are in the energy scales. There's Baji, also investigating the energy scales. And this is to show you kind of where everything fits. And this is also to show you, like, if you're doing ANITA, for example, which is over here. The ANITA experiment is over here. That's going to be complementary to something that is over here. So the neutrinos and the physics that ice cube would be sensitive to is going to be different. And ice cube is a different kind of probe than would be ANITA, just because ice cube is kind of over here in the energy regime and ANITA is over there. Or look at this, Dune is all the way over here. So what Dune is able to do is going to be completely different to where ANITA is. So this is very important to understand, that you're not trying to do everything. You acknowledge all the other experiments and all the other people who work on all the other things. And that way, you're also motivating your own case of where you are working, so that you don't have to do everything. So you acknowledge everybody in the field so that you can do your thing, and you can say, well, those other people are doing those other things. So that's another way of looking at this, okay? Okay, I talked too much. I have to take a little bit of a break and drink some tea. Continue to study this plot, and we will continue the discussion in just a second, also when my phone has more charge. So here it is. Oh, I want to clip this. Look at this. Oh, and let me know any questions. Thank you for joining the live, and let me know any questions you have on this topic. This is my thesis, so I'll probably be able to talk your ear off on the topic. So don't feel shy. It will give me a lot of pleasure to talk about this topic with you guys. So thank you once again for being here, and ask any questions at this point. And then we will keep on going. So, yeah. Hi, Baji.
Any questions? Scintillation detectors for secondary cosmic rays. Heike, yes! Wow, Heike already knows about the secondary muons that I will be talking about. Wow! Hi everybody. Hi Fuji. Hi Sashu. Hi Yave. Hi Hi Heike. Hi Lee. Definitely. Oh gosh. কি হয়েছে সোনা? I'm just charging my phone and getting my tea a little bit here. Baji mama. Hi baby. Hi Baji baby. Hi Fuji baby. Come. You want a snacky? এখানে খাও। আসো বাবু। Come. Sachi. the other thing is that it's important to know what we know, and it's also important to know what we don't know, so that you can do the things that we don't know and progress the research in that direction. So we will talk about that as well. What is it that we know, and what is it that we don't know? Also, it's common to do your PhD in one of these experiments and maybe a postdoc in a different one, you know, that type of thing. You want to be complementary even in your profession. Or your career, rather. Career path. So, we will see that the optical Cherenkov method that IceCube and Antares uses, it's going to be a different method for something like ANITA. Oh, wow. Some Bengal information. Hare Krishna movement is from Mayapur. Oh, wow. Yeah. Good to know. Now, Seth. Hi. Okay. Okay. I think I'm gonna. Yeah, I'm gonna go to the bathroom and then we'll continue because that should be enough charge in just a second here. We will talk about radio Cherenkov in just a second. Oh, hi! we're back. Sorry about the... Hi, Fuji. Hello, Reese. We're about to get started. As in, we'll continue. We will now continue to continue. We're charging the phone. Took a little break. And we have been discussing particle astrophysics. Sorry about the... We're back. Fuji, it's not quite time yet for your din-din. And you got some extra snacks. So shall we continue particle astro? Let's do that. I was just getting my situationed. You know, nose and congestion and such. So here I am. I'm back. Breathing in and out. I had to breathe in and out a little bit. A little bit of a breathing of ins and outs. How are you guys? I asked if you guys had any questions, and none of you had any questions. I must have explained everything really well, or not at all, because you didn't have any questions. How sad for me. Okay, so we talked about optical Cherenkov experiments in the form of ice cube and Antares. And yes, hello? Are you saying my name? Yes. Hi. Hello, Heike. So we talked about optical Cherenkov radiation type of experiments, both in the northern as well as southern hemisphere. Ice cube is at the South Pole, and it instruments the ice, a cubic kilometer of ice, and looks for astrophysical and cosmogenic neutrinos, especially in the energy regime of 10 to the 9 to 10 to the 17 eV or so. Antares is in the northern hemisphere. It instruments the Mediterranean Sea, not all the sea, but around 0.02 cubic kilometer of the sea, and it utilizes the water, the sea water, as a detection medium. Their food is about to fall. And 1 second, I gotta help them. Banerjee, yeah. Yeah, it's a Bengali name. Indeed. So Antares instruments the seawater to some extent and looks for neutrinos utilizing the sea water. And it's good to have these sort of complementary experiments in the two different hemispheres, one looking at the northern sky, the other looking at the southern sky. Not that neutrinos cannot go through the Earth as well, but sort of the noise and the things that they would deal with are different for the two experiments. And it's always good to have complementary experiments in complementary hemispheres, looking at complementary skies for these sort of rare type of neutrinos, because the more high energy the neutrino that you're looking for, the more rare it's going to be. And it's going to be kind of hard to look for something that's rare because the interaction that you are going after doesn't happen that often. And what may happen a lot is a bunch of noise type of things. The wrong muon or the wrong kind of neutrino could be part of your noise that you have to deal with. And whether that's at the experimental or instrumentation level or in the analysis itself, you're going to have to pretty much deal with all these other things that is not the signature that you're going after. By the way, if you're joining, welcome to the live, and can you hit the like button? I want to get maybe 20 likes. That would be really nice. So yeah, so we're looking at my thesis when it comes to particle astrophysics, because that's what I did my PhD in. And so that's what we're looking at. And this is public, so you can also find it. And I'm kind of happy to talk about it endlessly because this is what I did my thesis in. So it's sort of my thing. So thank you again for being here, and thank you for your patience. I've been kind of recovering from a cold, and so thank you again for bearing with me. So next, moving on, we will go to radio Cherenkov neutrino detectors. So I left you with looking at a bunch of experiments in that energy regime diagram that I showed with the big black arrow going from the left to the right. And towards the left were experiments that were looking for lower energy neutrinos, but even the lower energy neutrino energy ranges were sort of like a GeV range, 10 to the 9 EV, right? Let me double check to make sure I showed you the right thing. Yes, it's basically less than a GeV or around a GeV, up to a GeV level of neutrino energy is what is covered in that left side. In the middle, we had things like IceCube, Antares, and things like that, and we compared it to the energy number of around 14 TeV, which is the center of momentum energy of particles getting smashed together in the Large Hadron Collider. So a human-made accelerator can achieve energies of up to around 14 TeV or so. And so when we have experiments that are looking for neutrinos with around that energy or higher, those are considered the high energy regime. And then we had ultra high energy regime, which is neutrinos of energy over 10 to the 17 EV. And these were in the center of momentum energy range to be over 45 TeV, because the center of momentum energy is different from the overall energy of the particle. So if you're saying particle energy versus the particle within an interaction, its energy is going to be different, right? So sometimes when we compare, we might want to compare the energies of in a center of momentum kind of way, because the LHC, for example, those energies that are quoted, like 14 TeV, is a center of momentum energy. It's not the energy of a single particle. It's the center of momentum energy of that system. So that's why we might want to shift how we're quoting these energies. But if we consider the single particle, then the ultra high energy regime, it's going to be above 10 to the 17 EV. Sometimes these are called, like EeV is 10 to the 18. It's exa electron volt. That's the energy of the single particle. So we looked at the optical Cherenkov radiation type of experiments like IceCube and Antares. And now let's read about the radio Cherenkov. So radio Cherenkov neutrino detectors, this is where I focused, and my PhD is focused on this.
So, radio Cherenkov neutrino experiments look for ultra high energy neutrinos in the energy regime of over 10 to the 16 eV or maybe even over 10 to the 17 eV. The main challenge for detection by these experiments and a potential solution for detection are presented below. We also introduce two complementary radio Cherenkov experiments, ANITA and Askarian radio array or ARA. So a lot of these neutrino detectors in Antarctica are named after women, like sort of female type of names. So that's kind of kind of a well-known thing. Mine is called ANITA. The cousin experiment of ANITA is called ARA. My PhD sibling did his PhD on ARA. So in the same group where I did my PhD, we worked on a couple different experiments at least. ANITA was a big one. ARA is a big one. A little bit of even maybe Ice Cube, sort of tertiarily was involved as well. And we each basically got postdoc offers, me and my PhD sibling both. We each got postdoc offers in the Ice Cube collaboration. So you can see how we're all kind of related to each other. It's all in the family. And it just kind of depends specifically which one you're working on when. But our PhDs were in radio Cherenkov experiments. Mine was ANITA, his was ARA. And we, of course, collaborated, like we talked about everything, even if we didn't work on the other one's experiment directly. And in general, if you're getting a PhD in this topic, of course, you'll end up learning about all of the experiments and the cousin experiments of your own experiment, basically. So we introduced the two complementary radio Cherenkov experiments, ANITA and Askarian radio array, where they are on the energy scale as compared to other particle physics experiments is shown in that figure I left you with the energy regimes that I took some time to talk about. I took the time to talk about that because that's very important in multiple different ways in understanding the energy regime of the different experiments and what you get in the different energy regimes, but also to tell you about all the complementary experiments. The challenge of detecting ultra-high energy neutrinos is the next topic here. In this era of rapid growth in multi-messenger astronomy, ultra-high energy neutrinos remain undiscovered. So ultra-high energy neutrinos are still not discovered. One of the major challenges is that observation of these rare particles requires a huge detection volume. The interaction length of an EEV neutrino and a nucleus is about 300 kilometers. Less than 0.01 ultra-high energy neutrinos are predicted to hit the Earth per cubic kilometer per year, implying that to be sensitive to the ultra-high energy neutrino flux, we need a detection volume much greater than 100 cubic kilometers. So if you're getting 0.01 ultra-high energy neutrinos predicted to hit the Earth per cubic kilometer per year, then hopefully your detection volume is more than 100 cubic kilometers, because otherwise you're going to be looking for a very long time and not finding any. Such a huge detection volume would be too expensive to instrument using optical Cherenkov detectors, as optical light is attenuated over order tens of meters. Attenuated meaning that it will get diminished. So optical light gets attenuated over order tens of meters. So if you're looking at a very large volume, hoping to find these neutrinos, well, optical light is not gonna be able to be caught for a very large distance in that sense. Depending on the detection medium, of course, it is more attenuated or less attenuated. But as you saw, Ice Cube was only a cubic kilometer of ice. So when you're instrumenting a cubic kilometer of ice, and even then, remember how the photomultiplier tubes were very thickly instrumented in that cubic kilometer of ice. That's because optical light is not going to be something that you pick up on when you instrument very sparsely. you need that more thickly instrumented volume. Otherwise, you're not going to see it really, you know, in ice, that is. So now we will talk about the Askarian effect, a proposal known as the Askarian effect, stating that ultra-high energy neutrinos could be observed through their interaction in a dielectric medium, comes to the rescue. Fuji. Come, Fuji. So this problem with needing a very large detection volume is something that we have to address in radio Cherenkov or ultra high energy regime. And that's what we're going to talk about right now. So what is the Askarian effect? Basically, the principle is that a relativistic ultra high energy neutrino would interact with a nucleus in a dielectric to produce a particle shower, traveling in the medium at a speed greater than the speed of light in the medium. So that particle shower that's created in the ice, in the case of, say, Cherenkov happening in the ice, or sorry, this interaction happening in the ice, that particle shower will then travel in the medium at a speed greater than the speed of light in the medium. Not the speed of light in vacuum, because that's a constant and you cannot go above that speed, but the speed of light in the medium of ice, maybe you could go at a higher speed than that. The particle shower would mainly consist of photons, electrons, and positrons. Very simple. So basically, when an ultra high energy relativistic neutrino, because remember, a neutrino is a very low mass, small, tiny little particle that does not interact with very many things, but we're talking about a very high energy, ultra high energy neutrino, which is going to be there's this big noise outside with the traffic. Okay, so we're talking about a relativistic ultra high energy neutrino because, so it's going to be going at a very high speed because it's a very low mass particle. So if it's ultra high energy, it basically means that it's going at a relativistic speed. Okay, so the principle is that a relativistic ultra high energy neutrino would interact. So at that point, basically, even though neutrinos for the most part don't interact with most things, but such a high energy neutrino is predicted to interact with other things, but the cross section is still low. It's not like it's going to happen all the time, but we do have some idea for, depending on the energy of the neutrino, what is its cross section for interaction with particles. And will, for example, there's papers on this. I think my advisor actually wrote one of them. So she is a particle physicist. Her name is Dr. Amy Connolly, and you can look her up. She has work on this herself, where basically we know that neutrinos are weakly interacting and they don't interact much generally. But as we get higher and higher energy neutrinos, theoretically, we expect them to interact, but with certain cross section. And we have seen that the cross section of this interaction is going to be higher if you have a higher energy neutrino, where you might even get a high energy neutrino to be stopped by the Earth. Because most of the time, neutrinos that are lower energy will just go through the Earth. What does that mean? Going through the Earth means that you did not interact the whole time with anything as you went through the Earth. Like all of the mass of the Earth is in your way and you just go through it like it's nothing. It's transparent to you, right? That just means that you're so introverted, probably so tiny, and probably just didn't give a frick about anything. You just go through the Earth like it's transparent to you. And that's what most neutrinos do. This is also the reason why some people thought when they found dark matter, as in they found that there is this dark invisible matter that we cannot account for, we don't know what it is, but there's this extra matter in our own galaxy and in the universe that we don't understand. People thought that this dark matter could actually be neutrinos, because neutrinos kind of behave similarly in that sense. Turns out neutrinos are probably not dark matter, or they don't account for most of the dark matter in our own galaxy or elsewhere because they're too low mass. But this is the reason why. Neutrinos, for the most part, could probably just go through the Earth like it's nothing. Okay, so, but now you have to remember, we're considering an energy regime that's very extreme. We're trying to capture or detect the signatures of neutrinos that are very high energy, coming from some very exotic high energy type of events in the sky far, far away. Extragalactic origin, maybe from another universe. I think there are many millions other universes somewhere expanding different directions in the dark matter. That could be, yeah. But basically, as far as, so I don't know about other universes, but for sure that the neutrinos and the cosmic rays that we have been discussing kind of in this particular live stream in my thesis are often extragalactic in nature. They're not really predicted to be coming from our own galaxy. They could, but those, remember that first paragraph I read from my thesis today? These exotic events, such as, for example, gamma ray bursts, happen like billions of light years away. They happen at, I think I said, what was it? It was like some gigaparsec away, right? A gigaparsec away, which is around, I have to double check this, but it was like 3 billion light years away or something like that, some huge distance away. So some of these exotic events, because they happen so far away, by nature, they're happening in other galaxies. They're not in our galaxy, and they're not from our neighboring galaxies even, right? So we are in a more boring part of the universe, if you will, in that sense. Partly why we're here is because it's boring and it supports life, right? Can you imagine if we were super close to like a gamma ray burst where all these like this big kind of explosion is happening and it's spewing material into the sky, and like we could get hit with that and we would not be here, right? So we evolved on this earth at this time and in this way because we're in a relatively boring part of the universe, which means also that our astrophysics is going to be a little bit boring, and the interesting astrophysics that we might be interested in would be happening kind of far away from us by nature, because we are here, we're alive, touch wood, because gamma ray bursts happen far away from us. Okay, so what that means is that if we were to get a neutrino, though, say from such an exotic big energy event, that neutrino is predicted to have a very high energy. And that neutrino, not the neutrino from the sun or some other neutrino, but that neutrino, which is from that big energy event, is supposed to have a very big energy. And that neutrino will interact differently. It will have a higher cross-section of interaction in our Earth's ice in Antarctica. So the neutrinos that we were going after in my PhD experiment are not regular neutrinos. They're from very exotic events. And from that faraway event, that big energy event, that big energy neutrino with a certain cross-section predicted is supposed to interact in the Antarctic ice of our planet. And hopefully my detector is ready to detect this signature when that happens. So we're talking something which is like very rare, very exotic, if you will. And so that's where we are at, okay? Now, this neutrino, what will it do? It's a very high energy neutrino. As it meets with our ice in Antarctica, let's say it's here, and let's say it's ready to interact with the Antarctic ice. What it actually does is interact at that level, with that high energy, with that relativistic speed, it's going to actually interact with a quark within the Antarctic ice. And after that interaction, it will create a particle shower. Like it's going to really cause some chaos with those energies and those speeds. And it will create a particle shower in the ice of Antarctica, which will be made up of photons, electrons, and positrons. And that particle shower will then be traveling through the ice at a speed greater than the speed of light in ice, producing Cherenkov radiation, because that's what Cherenkov radiation is. When a particle shower goes through a certain medium at a speed greater than the speed of light in that medium, you get a certain phenomena out of that, and it's called Cherenkov radiation. Hi, Peter. I'm here, been listening to you. Good. Glad you're here. I'm having some bad days too, so I'm right there with you. I'm having some bad days and I've had a cold. Yes, a particle sonic boom. Indeed. Okay, so when this Cherenkov radiation, yeah, I'm still sick, but I'm hopefully, recovering, trying to. So the particle shower would mainly consist of photons, electrons, and positrons as it travels through the dielectric, which is the ice. Because remember, I mentioned at one point that to do this type of detection, you basically need a dielectric. The dielectric could be ice, it could be water, it could be salt, it could be something, but it better be a freaking dielectric, okay? As it travels through the dielectric, the particle shower develops about a 20% negative charge. This happens primarily due to Compton scattering of electrons in the medium, so electrons leaving the medium and joining the shower, and secondarily due to annihilation of positrons in the shower with electrons in the medium, so positrons leaving the shower. So we've created particle shower. The neutrino's job so far is that it created a particle shower. It basically created some chaos. It comes to Earth from some exotic event far, far away that is not near us at all, probably, definitely extragalactic. And it creates chaos as soon as it hits a quark in our Antarctic ice. For the case of my experiment, it could be something different. For the case of other experiments, it could be the Mediterranean seawater if it's in the northern hemisphere. But as soon as it meets with a quark, it doesn't just meet with a quark, it creates a freaking chaos because it's going at a very high speed, it's very high energy, relativistic at that point. It creates a particle shower situation, okay? And we'll get into the geometries of this in just a second. But this particle shower consists of photons, electrons, and positrons. And this particle shower starts to become negatively charged. There is a charge asymmetry in this shower. It's not got the same amount of positive charge as negative charge because there's more things producing electrons and than positrons. Basically, there's a process for making more electrons, which is Compton scattering, as in the electrons from the medium join the shower. And then there is a process basically reducing positrons because positrons in the shower that has been created can annihilate and leave the shower. And now there's more electrons than positrons. In general, too, as you know, in nature, there are more electrons than positrons. So it's not very surprising that the shower, after creation of electrons and positrons, you end up with more electrons because there's basically more processes making electrons than there is positrons. So there's a signature of some sort which remains in the ice. So right now we're just talking about the particle shower. We will look at the signature in just a second here. But basically, the science of how this detection works is that the neutrino has entered the ice, it has hit a quark, it has created a chaos of an interaction, which leads to causing a particle shower at those energies and that relativistic nature of the neutrino, this particle shower mainly consists of photons, electrons, and positrons as it travels through the dielectric. So also remember, this dielectric medium is itself participating in this whole story, because if the dielectric medium did not provide more electrons to the particle shower that's moving through the ice, then we might not have enough negative charge for this whole thing to happen, right? So listen to this carefully. As it travels through the dielectric, the particle shower develops a 20% negative charge. This happens primarily due to Compton scattering of electrons in the medium, so electrons leaving the medium and joining the shower, and secondarily due to annihilation of positrons in the shower with electrons in the medium, so positrons leaving the shower. As this charged particle shower, so now keep in mind, it's not just a particle shower, it's a charged particle shower. Charged particle shower, it has a negative charge. If there were same number of positrons and electrons in the shower, this might not be possible. But because it's got more electrons, it's a charged particle shower. As this charged particle shower travels through the medium at a speed greater than the speed of light in the medium, not greater than the speed of light in general in vacuum, because that's a constant and you can't do that, but it travels through this medium at a speed greater than the speed of light in the medium, Cherenkov radiation is produced. So Cherenkov radiation is produced when a charged particle shower is going through a certain dielectric medium at a speed greater than the speed of light in that medium. Now, there's further science and further geometries. If this Cherenkov radiation is observed at wavelengths larger than the shower's transverse dimension of about 10 centimeters, so this shower size matters a lot as well. The shower size is about 10 centimeters, okay? Depending on the medium. In this case, it's about 10 centimeters in the ice. If you observe the shower, so the shower is happening whether you observe it or not, let's just say, and the shower size in the ice is around 10 centimeters, but you have to observe it, but not just observe it, you have to observe it at wavelengths that are greater than the shower's transverse dimension of about 10 centimeters, then it would be seen as coherent waves in radio frequencies. So because of the 10 centimeter, you basically get radio waves when you do the, because that's like a wavelength, right? So when you do the frequency, get the frequency of it, basically this will produce radio waves coherently. Because Cherenkov radiation is basically light, right? Because of this particle shower that's now charged, going through the ice at a speed greater than the speed of light in the ice, you get Cherenkov radiation. But Cherenkov radiation could be coming out in all different wavelengths. You have to get the Cherenkov radiation, yes, you have to get the Cherenkov radiation coherently and in a way that you can actually observe it. And you have to do the observation as strongly as possible. Like you want this signature, right? But you want the strongest part of the signature. And the strongest part of the signature is going to be where it's coherent. And we worked it out that the geometry gives us that you would get strong coherent waves in radio frequencies. Exactly. So the signature is radio waves. ResearchGate has information from your experiment. Yeah, we have several papers. Yes, we have a lot of papers on this, but some of them might be on ResearchGate, but they should all be on archive.org. But yeah, we have a ton of papers on this whole thing. So the signature is radio waves, exactly. So this whole detection method is basically that an extragalactic, ultra high energy, relativistic neutrino will enter the Antarctic ice, will interact with a quark in the ice. Because it's very high energy, we predict some level of interaction. Not everyone will interact, but there will be some cross-section predicted of interaction between this very crazy ultra high energy relativistic neutrino and a quark at that point. It's not like it just meets with the nucleus and is all happy-go-lucky. It will hit a quark like a quark has never been hit in its life, and it will create a chaos of a particle shower, which is made up of photons, electrons, and positrons. And because of Mother Nature and Compton scattering and positron annihilation, there will be more electrons adding to the particle shower as it goes through the ice than positrons, giving it a charge. It will develop an overall charge asymmetry of around 20%. And now we have a charged particle shower going through the ice at a speed greater than the speed of light in that medium, giving us Cherenkov radiation. Not only that, this Cherenkov radiation will be coherent and strong in radio waves because of the geometry of the particle shower, which gives it around a 10 centimeter transverse length. Yes, because of the ice medium. That's one of the reasons. Antarctica also gives us ice and a polar vortex and less noise and the southern sky and less people, thank God. Hi, Kaya. Antarctica is because of a lot of reasons. It's because it gives us a ton of ice, which is the detection medium for this particular method. It gives us the polar vortex, which helps us to launch a balloon mission with the help of NASA, and utilizes that polar vortex during the austral summer to launch the mission and look down on the ice with our radio antennas looking for a radio wave signature of neutrinos in the ice. Gives us all that ice that the neutrinos would interact with. Ice is also radio transparent to a large extent. And Antarctica has less people, less noise overall. There's reasons for hanging our detector on the balloon as well. You could either instrument the ice, like put your instrument in the ice itself so that you can pick up on a signature like this, or you could do where you put your instrument on a balloon and launch the balloon, and then you get to survey more ice at any given time. So there are pros and cons for how you design your experiment. And generally the way you design it kind of complements other experiments that are already existing. So those are all the different reasons. Those are some of the reasons. There might be even more reasons. But yeah, the less anthropogenic noise, as in less human-made noise, all of the Antarctic ice pretty much is the main reason, I would say. Ice is dielectric. It allows for this type of interaction. Antarctica is 99.9% ice. Like, it has very little rock. If you're somehow able to instrument all of Antarctica, of course, Antarctica is also melting. That doesn't help, but, you know, Antarctica is a ton of ice. It really is very pure in that sense. It's it's mainly ice. The rock that Antarctica has is volcanic. Antarctica has some volcanoes. I saw this volcano every day when I worked there. Mount Erebus, southernmost volcano. And it's an active volcano, and it creates like precious crystals, apparently. So that's the whole thing there. But anyway, it's the ice, it's the lack of noise, it's the polar vortex, and also the logistics. Antarctica is a great place for science. Antarctica is not a country, right? You sign a treaty and you go there and you promise that you won't bother the penguins and the seals and be a good person and not litter and all this stuff. It's set up for scientific missions, so this experiment can also be done in Greenland. There is a Greenland Neutrino Observatory. So, you know, there are other efforts. Antarctica is not the only place where these types of efforts exist. But what people found 20, 25 years ago, you know, when this type of field was kind of getting off the ground, is that Antarctica was particularly suitable in terms of logistics as well. Believe it or not, like, they found it easier to go to Antarctica and do this experiment than go to Greenland at that point in time. So I rest my case that the northern hemisphere is highly overrated. Most of the population lives here, so of course it is. So let me show you a picture. So this is the interaction. This is the cartoon I've made for you guys. Well, for my thesis to get my PhD, but at this point for you guys, showing you the interaction that I was just talking about. So a UHE neutrino, an ultra high energy neutrino, could start a pancake shaped particle shower in the ice. See, neutrino coming in. Ultra high energy neutrino induces pancake shaped particle shower. This pancake shaped this is the shower from the neutrino hitting a quark in the ice. This shower develops, it's mainly made of electrons, positrons, and photons. And remember that it develops a charge asymmetry because of the lack of positrons. In other words, there's more things making electrons than positrons. The lengths are as follows. Each layer is kind of like a few centimeters thick. The transverse direction is transverse, meaning the direction that's perpendicular to the neutrino coming in. That direction size is around 10 centimeters, and the overall thing is 1 to 10 meters. Because of the transverse size being 10 centimeters, if you're looking at this whole thing at a wavelength greater than 10 centimeters, then you will see the signature to be coherent. So the strongest RF emission or radio wave emission happens at that type of wavelength, and hopefully you're over here, ANITA detector in the sky, looking at this thing. It will do a little bit of a refraction here in the ice and go straight towards, hopefully, my experiment's detector. And that's how we hope to catch the detection or catch the signature of such a neutrino in the Antarctic ice. I know it's a little involved process, but that's to be expected in all particle physics experiments. That is not too bad, actually, as far as particle physics goes. Okay. So that's the whole plan for this. We will see how it all unfolds over time, but that's basically the geometry and the setup of this type of detection technique. And remember, the detection technique may be similar for other experiments, but it'll be a little different. For ARA, Askarian radio array, they put the detectors directly in the ice. They don't hang their detector from a balloon and launch it in the sky. They put it right in the ice. So that's a different kind of experiment with a different sensitivity and a different plan and setup. And it's complementary to ANITA. Every experiment does their own thing. Ariana is yet another experiment, slightly different again in its own way. And remember, these are the radio ones. ANITA, ARA, Ariana are radio Cherenkov type of experiments. Whereas IceCube and Antares, the ones we mentioned earlier in the live stream, are optical Cherenkov experiments. They look for optical signature of neutrino interaction. We look for radio signature of neutrino interaction in the ice. So the overall science is similar, but the details are a little bit different. Okay? Any other questions? Okay, but yeah, Antarctica having a ton of ice, meaning the detection medium, less noise, and being radio transparent, and having the polar vortex. Those are the main reasons for Antarctica, okay? And it's just cool, pun intended. I love that I went there. Thank you, universe. It was both deduced and we did experiments to figure that out. There's a paper on it. We did experiments to figure it out, but it was also deduced. So The paper on it, let me just... Oh, not that paper. So we went to a salt mine, not me personally, but my senior colleagues went to a salt mine, I believe, and they made measurements of this type of thing. Like, you know, before we go to Antarctica to measure it, you better be able to like actually make a very great case for the fact that this could be happening, right? So they proved it out first in like a much smaller scale using a different dielectric, because they're not going to let you just go to Antarctica, you know, unless you have a really good case and a really good reputation and already established setup. They don't just let you go to Antarctica. Like even tourists have a good time, have a hard time going there, right? You have to take a cruise or something. You can't just like show up to Antarctica, right? With your like radio antennas. You have to have a very nice big process in place for it to be acceptable to go and do an experiment there. And for that, you probably have to go through a lot of hoops. And yes, I had to sign that I would respect the treaty. We all had to do a training before we went to Antarctica. So so the way we proved out that this thing is something we expect to be able to detect there is a paper on it. It is called, I know we went to a salt mine. Where was it? In Slack? I think it was. Stanford Linear Accelerator something. Let me just find it. Oh, why am I not control Fing? Am I crazy? We wrote so many papers on this. But this particular one I do want to mention. Oh, by the way, Askarian is a guy and he has a paper. So if you want to read about just the Askarian effect, then there's a paper written by G.A. Askarian, the person, and it's called Excess Negative Charge of an Electron Photon Shower and its Coherent Radio Emission. And it's a reference in my thesis. It's in JETP. I forget exactly what that is, but it's a paper. I think you can probably just find the PDF of it if you Google that. So it's called Excess Negative Charge of an Electron Photon Shower and its Coherent Radio Emission by Askarian himself. And you can see that we already had this. We knew that there is this excess negative charge from a shower that would be happening, and that it's expected to give us coherent radio emission. And because of that, we expect to be able to pick, like, that's why we designed the experiment around that. Okay. But I'm trying to find the paper on our Slack work. Scooby-Dooby-Doo, where are you? Are you serious? If I did not reference the Slack paper,
then I am confused. That's okay. Whatever. We'll keep going. But there's definitely a paper on that too. Our early work paper, sort of the history of ANITA and the history of this whole thing, of this whole thingamawitch. Anyway, we'll keep going. Oh God, this thesis is so long. Who wrote it? Okay. That one's done. Okay. Now we're gonna talk about ANITA, more specifically. So we just talked about the Askarian effect, and now, henceforth, we will talk about ANITA. My ANITA. Me. So we're gonna talk about me. Fewer electrons than protons. In the shower, you mean? No, in the shower it's fewer positrons than electrons, is why we have the charge asymmetry. Because the particle shower had photons, electrons, and positrons, and there are fewer positrons, which is positively charged, than electrons. Positron is simply the antiparticle of electron. So, no. There are fewer positrons than electrons, so you have a negative charge asymmetry. Okay? You have more negative charge. Because the particle shower initially has photons, electrons, and positrons, and as it travels through the ice, if it's making more electrons because of Compton scattering and losing positrons because of annihilation of positrons to make, again, electrons rather than positrons, then it's going to have more negative charge. Okay, so now we'll talk about ANITA. ANITA is an experiment dedicated to discovering ultra-high energy neutrinos via the Askarian effect, utilizing the Antarctic ice as the necessary dielectric target medium for neutrino interaction. So the ice is the dielectric target medium as in the stuff that the neutrino will hit, where ANITA's sensitivity lies in the energy scale as compared to other experiments in particle physics and particle astrophysics is presented in that figure I showed you earlier with the big black arrow and all the experiments. A cartoon of an ultra-high energy neutrino coming into the ice and starting a particle shower that leads to Cherenkov radiation emitted coherently and at an angle of around 56 degrees is shown in that cartoon I just showed you. ANITA looks for radio Cherenkov signals with an array of radio antennas. The ANITA detector is hung from a helium-filled balloon and launched from near McMurdo Station in Antarctica during the austral summer. After it is launched, ANITA floats up to an altitude of about 40 kilometers and utilizes the polar vortex to fly in roughly circular orbits over the continent of Antarctica. At its float altitude, which is where it's kind of stopped climbing up the atmosphere and just floats up there, up-to-do, at its float altitude, the balloon, upon a gradual inflation, so it gradually inflates to its full size. When you first launch it, it's not fully inflated, okay? At its float altitude, the balloon, upon gradual inflation, is bigger than the Ohio Stadium. I had to say something about the Ohio Stadium given that I went to school there. Ohio Stadium is simply a very big stadium of football games. I don't know. I've only been there once to see Taylor Swift. It's a big football stadium.
There have been 4 flights of ANITA so far. I was on the 4th one. These are summarized in figure 1.7. We will get to it. During its flight, at any given time, ANITA can scan about 1 million cubic kilometers of ice. This makes ANITA the neutrino detector with the largest instantaneous detection volume. The use of the radio Cherenkov technique goes hand in hand with covering a detection volume that is orders of magnitude larger than what is possible with optical Cherenkov techniques, such as in ice cube. So yeah, the whole thing about being a balloon experiment and looking for radio Cherenkov techniques, we know radio waves are not as attenuated as optical waves are for light. And especially ice is very transparent comparatively to radio waves than to optical. So because of the unattenuatedness of the radio waves, that also makes it makes it possible to have such a big detection volume. So the use of radio Cherenkov technique goes hand in hand with covering a detection volume that is orders of magnitude larger than what is possible with optical Cherenkov techniques, such as in ice cube, which is 1 cubic kilometer of detection volume. Radio waves have attenuation lengths of order 1 kilometer. So the attenuation length of a radio wave is like a kilometer in ice. A kilometer, while optical light attenuates over orders tens of meter. For ANITA, radio waves from neutrino cascades are produced in the ice, but then have to travel 40 kilometers through air before they can reach the detector. Therefore, ANITA is sensitive only above about an EeV neutrino energy, so it is looking for the rarest neutrinos. A cartoon of radio waves from a particle shower caused by an ultra-high energy neutrino in the ice reaching the ANITA detector is shown in figure 1.8. So we will look at that. Let me tell you about our flights. So we have a summary of ANITA flights in table/figure 1.7. So our first ANITA flight was in the year 2006-2007, ANITA 1. The length of this flight was 35 days, and the status of it at the time of writing this thesis was that the data analysis was published already at that time. Hi, Nicholas. Then we had ANITA 2 launched 2008-2009. This was a 30-day flight. We also analyzed this flight. Then next we had ANITA 3 in 2014-2015. This was only a 22-day flight, and we worked on analyzing the data from this. I myself was involved in that because I was involved in the hardware and launch and all of that for ANITA 4, meaning that ANITA 4 was underway, meaning that we had data available from ANITA 3, which had to be analyzed. So that was part of my thesis as well. And then in 2016, we launched ANITA 4, which I was part of, and the length of this flight was 27 days, which is so much better than ANITA 3. And then we also worked on, we started to work on analyzing that data. Probably ANITA 4 was analyzed more after I graduated, you know. But anyways, that's the summary of the ANITA flights. After ANITA 4, the ANITA program was canceled because ANITA 4 did so well. And I think they proposed and basically had to start a new program. And so ANITA, as ANITA, is kind of like done. Hi, Nicholas. I miss your kitties. Oh, they're here. We'll take a look. Okay. Okay. Are you ready to see my cartoon of ANITA now?
Hi, Alf Jose. Warm Christmas regards from Germany. Yay! Welcome to Germany. How are you? Thank you. Merry Christmas. Merry Christmas to Germany. So, here's the cartoon showing you the Antarctic ice sheet and the concept of the detection of ultra-high energy neutrinos with ANITA experiment. So there's the ice cartoon. Antarctic ice sheet is lots of ice and it's radio transparent. So you'd have the neutrino coming in at this sort of angle. Then you would create the particle shower like we mentioned before. Particle bunch emitting electromagnetic waves. You would get the Cherenkov radiation, remember? Then it would go like this and it would get refracted. Hopefully ANITA is over here because ANITA isn't always flying, right? So this would also be dependent on when ANITA is flying. And so then there's the detector with on the big balloon. This is not to scale. The balloon is much bigger than the detector. This is at a 40 kilometers altitude from the Earth. And yeah, that's how this whole thing would work. So take a look at that. That's what we are talking about. I need to take some sips of my tea actually. So let me pause here for a second and catch up with you. Hi Alf, hi Nicholas, hi Heike, hi Reese, hi everybody. How are you guys doing? Oh my gosh, I am so happy. I am so very happy that I'm looking at ANITA's cartoon. I'm looking at my childhood. Hope you like my cartoon. Thank you for liking the live. Nicholas, how are you? Thank you so much for being here. Welcome to the live. Thank you for liking the live. We want to get 20 likes if possible. Thank you. I'm fine, thanks. Alf Jose. Any questions? Any questions? Ooh, look at my pendant. That's the little lock. This is my new necklace and pendant from Spotmart, who is going to be the sponsor of this live stream. They sent me the jewelry by mail, and I got this pendant which says B for Baji. I think it says B. What do you think? What does it say? B, right? And these earrings. Nicholas, you have a question? Tell me, please. Pray ask your question. I'm ready.
I think the next part of the thesis is about aura. Never mind, I don't know. Okay. Ooh, let's do something fun. When is you guys' birthday? We'll do something light for 1 second. Type your birthday month. I'm trying to be more relatable. God. Oh, wow. In quantum failures, how large is a wormhole? And how long could it actually stretch before it tears apart and creates another universe? So, let us first define a wormhole. We mentioned this earlier. So I just want to revise what we had gone over as regard to wormholes. Okay. Because remember, it was kind of exciting. We got the first weird. Interesting. I can't find it anymore. But yeah, we read a little bit about this, not a lot. So we didn't really cover this in a great detail. So long story short, I don't think I know the answer of what you're asking. But I did want to address what a wormhole even is. Yes, but oh yeah, here it is. I wanted to talk about it in a better way than I can do it, you know? So, thank you, Heike. Heike is helping. So, Einstein and Rosen, remember we talked about this from this book, Einstein's Cosmos by Michio Kaku. Einstein and Rosen proposed a novel way to achieve such a solution. They started with two Schwarzschild black holes defined on two parallel sheets of paper. By using scissors, one could cut out each black hole singularity and glue the two sheets back together. Thus, one obtains a smooth singularity-free solution, which Einstein thought might represent a subatomic particle. Thus, quantum particles can be viewed as tiny black holes. This was just what they thought. We don't know if that's true or not. This idea was actually revived in string theory 60 years later, where there are mathematical relations that can turn subatomic particles into black holes and vice versa. Hi, Crazy Sick. Wine. Hello. I could do with some wine right now myself, to be honest. The Einstein-Rosen bridge, however, can be viewed in another way. It represents the first mention in the scientific literature of a wormhole that connects two universes. Wormholes are shortcuts through space and time, like a gateway or portal that connects two parallel sheets of paper. The concept of wormholes was introduced to the public by Charles Dodgson, otherwise known as Lewis Carroll, the Oxford mathematician and most famously the author of Alice in Wonderland and Through the Looking Glass. When Alice puts her hand through the looking glass, she is in effect entering a kind of a Einstein-Rosen bridge, connecting two universes, the strange world of Wonderland and the countryside of Oxford. It was realized, of course, that anyone who fell through an Einstein-Rosen bridge would be crushed to death by the intense gravitational force enough to rip their atoms apart. Passage through the wormhole to a parallel universe was impossible if the black hole was stationary. It would take another 60 years before the concept of wormholes would occupy a key role in physics. So that's all I know really about wormholes. Like, sort of along those lines is all I understand about wormholes. They're not my expertise, and I don't know anything about them ripping apart or how long before they would rip apart and how long before, you know, going into the next universe or something like that. But we did mention them briefly on one of these live streams, so I wanted to find the part again where we talked about wormholes, because I thought that that little snippet was kind of nice and cool to read about, and how the wormhole is really the Einstein-Rosen bridge. Rosen was one of his students, and so I thought that was worth like revisiting, just because we had kind of talked about it, and the fact that Alice in Wonderland is basically talking about wormholes. But yeah, sorry that I don't have much more than that for you on wormholes at this time. But it may come up again as we do more discussions of cosmology and things like that. So stay peeled on that. Like, stay tuned for that, and maybe it'll come up again. Yeah, I need to find more books by Kip Thorne. He'll definitely have it. Yeah, you're right. So Heike, Heike is helping out here. Thank you, Heike. Heike is saying Kip Thorne has some interesting views on time travel using wormholes. I need to find Kip Thorne's. He has some books that I need to find for sure, because those would be interesting in general. Nothing tastes better than the red wine. Most definitely. You like red or white? So this is a great question by Crazy. So Flowey, Fuji is pushing things off of the counter. I'm just looking at what exactly he's pushing and whether it's breakable or not. Okay. There's a honey there. There's the whey protein. Okay. So I like red when it's cold and white in the summer. I'm very simple. So Crazy Sick Wine, do you have any wine recommendations for me? And feel free to send me some. If you're like a wine dealer, feel free to send me some wine, man. I love wine. Wine is like my choice drink. Like, I'm sick now, so I probably shouldn't be drinking any wine, but I like it. I like to drink red. It like makes you warm and fuzzy in the winter, and I like whites in the summer. So I probably end up drinking more red because I'm in Boston and the summer is like 2 months long. So, 1 second. Hello, Fuji. Fuji Babu.
I think Fuji wants to be fed his dinner. I might do that right now actually with you guys. Because he's being very let me charge the phone and give them their dinner. Because they're being very You almost said it, and I'm glad you didn't. I said what? What did I not say? Okay, I'm gonna charge the phone and give them their dinner, okay? Oh, Shachi Mama! Shachi Mama is so sweet. And she's so happy that she's gonna get dinner now. She's such a sweet mama. As a mama, you're sweetie. You're a sweetie. You're a sweetie. Oh. Love you, mama. Come. We will get your din din. Baji! Baji Baba. I might eat some soup with you guys too. Y'all want to eat some soup together? Come. Okay, beta. I have to wash my hands. Look at them. They're ready for their din-dins. Okay. 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 I'm trying to give it to you. Fuji, come. It's coming, Baji. They eat so fast. Oh. Eating so fast. You're eating so fast. Fuji, slow down. I have to give his food in installments. He eats too fast. Aste khao, babu. Okay. Are you guys still around, Lee? Here you go. Sushi. It's kind of cold still. Really? This may be the longest live stream. You have almost 5 hours. Okay. Wow. Well, I started early. I think I'm gonna keep on starting early so that I can utilize this time and we don't have to stay up so late, and mainly also because it's been so cold downstairs. I probably like need to go to bed early at night. So longest live stream. Yay! Nicholas, your messages are all not showing up. Okay. I think I'm gonna make some soup. What do you guys think? I've been coughing and I still have to recover. So I think I'm gonna make some soup and I can eat it with you guys. I'll make some soup. Y'all get some food too. Y'all get some food too. Look at this Baji baby. Baji baby. Oh. happy after your din din? Baji's happy. Baji's happy. Sachi mama. I love. Let me show you. I want to pick up Sachi mama. It's a drop soup and rice crackers. Oh. Sachi. Oh, she's using the bathroom. Okay. Baji. Oh. Hi. Cuddle, cuddle, cuddle. Cuddle, cuddle, cuddle. Cuddle, cuddle, cuddle. Cuddle, cuddle, cuddle. Cuddle, cuddle. Hope you enjoyed Baji's belly. And now you can see Suji. That one is Baji. He's a boy. This one is a girl. She knew that I would pick her up too, so she has gone to this height. But Baji let me. Baji he's back to his stool. Baji likes attention. Cuddle, cuddle. Oh, look at Suji. Look at how fast she's running now. Look at that. Chasing each other. Can you believe this level? Fuji's over here, giving me company. Wow. Wow, guys. I wonder if they'll come running back too. Fuji Suji Baji. Alright guys, as I make my soup, you can look at my ANITA cartoon. And then I'll make soup and keep chatting. Where is my ANITA cartoon? There. I like this way of presentation. Using the laptop, it's nice because, you know, I tried to figure out like streaming with my slides, and that was actually very difficult. Everything was too slow. And so now I'm showing the slides like this. The slides as in the pictures and things like that. There. You can look at that while I make the soup. Okay. Fuji Babu. Oh gosh. Oh my god. This keeps keeps becoming excuse me. What? Okay. Hi, Flowey. Alright, I'm gonna eat this chicken and home-style noodles. Yay! Excusez-moi. Oh, good God. I have to stay quiet for a bit. Eat the soup and carry on. Carry on with the carrying on. Okay, we'll go over there. Alright, so everything off. Unplugged. Yes, unplugged over there. Good. Checked. Good. Nothing out. Good. Before I sit down. Okay. Get that. Off. And off. Off. And off. Off. Off and off. And off. Off and off and off. Off and off. Off and off. Alright, children. Fuji Suji. Mama's gonna eat soup. I'm gonna add some pepper to this. Look at my soup. Sick food. Oh, look at where Baji and Fuji are. Okay, we will now eat together. Yum yum. Indeed. Y'all should get some food too. You can get me. You can get some food and see if you have any questions from the earlier parts. I might eat at the counter. Yeah, over here. Oh, no, like that. I can sit up here. There. Cool. I like this bowl. It's chicken soup. I've been sick. See? Chicken noodle soup. Looks like that. What you nibbling on? How you doing? Bobby Kennedy? Why? I don't know the history of that. It's been snowing today too. It's definitely chicken noodle soup weather. Yeah, that's what everyone says, right? Eat soup. Yeah. This has noodles. I like it. Mm. Like Indian food? My favorite Indian food is probably like a bhindi masala, aloo. You know, like yeah, I like goat, but I love aloo bhaja and dal. Just a simple Indian meal. Like dal, rice, aloo bhaja, bhindi. Those are my favorite Indian dishes. Hi Niraj, I've been sick. I eat just unhealthy meatballs, smashed potatoes, milk. That sounds great. I love mashed potatoes. There's Baji. Oh. Thank you. I'm trying to recover. Flawless. Y'all didn't tell me your birthday months. Tell me your birthday months. Did I get 20 likes? Hiking? I got 20 likes? Oh my god! धन्यवाद जी. लाइक नंबर 20 मेरा है. शुक्रिया. Likes. Nicholas says Aries. Heike, is your birthday in December? Crazy Sick One says that was Milo. 21? Thank you for liking. Heike, your birthday's in December? Wait, how do I know that? Have you told me before and I just remember it? Gemini. I'm a Libra. We're related. Air signs. My face looks weird. You told me? Did it already happen? Heike, or is it gonna happen? Oh, it already happened. 1st December. What? Sagittarius. It was a pleasure meeting you, Niraj. Gemini. How was your day? My day has been on the live stream, so पीछे जाकर देख लीजिए क्या क्या किया आज. पढ़ाई की, टीचिंग की, खाना खाया, चाय पी, बच्चों को खिलाया. मंदिर, मैं मंदिर ज़्यादा नहीं जाती. Not a mandir kind of person, really. My mandir is at home. Heike, what did you do for your birthday? One second. That sounds amazing. Coffee and cake. Now I want cake. Now I want cake. Should I get cake? No, it's too snowy outside. Agnostic. Remind me what that is. Actuary. Remind me. What is that? Because I've forgotten. Is that like financial work? statistics. Maths to minimize risks. That sounds boring as heck. No thanks. Math to minimize risk. Thank you. Thank you for reminding me what that is. I hope I never have to do that job. Y'all should go to my PayPal and donate to my channel so that I never have to do that. And I can buy myself chicken noodle soup with YouTube money. I'm willing to eat chicken noodle soup every day. I am a princess. Except not really. I'm a queen. I have my own empire. The empire of my household, run by me. I need to wash my hair. There's a knot in my hair. But because I'm sick, I've been sick, I can't even wash my hair. I can't go to the gym. I can't swim. It's so cold. Sorry, that was my moment of... Thank you guys, everybody, for joining. Really appreciate it. Thank you for having soup with me. Thank you for listening to my physics talks and letting me share particle astrophysics with you, which is also my thesis today, as in my thesis every day, but today I talked about it. Thank you for looking at my jewelry. If you want to order any for yourselves or your girlfriends and wives, or friends and moms and sisters, I'll link to it in the description later on. I can't do it right now magically because of whatever reasons. Here's the pendant. It says B. Here's the earring. Thank you for hanging out and giving moral support and looking at the kitty cats and liking the live and giving me 22 likes. I get a little frustrated by jewelry, actually, if I'm being totally honest. My intelligence is my jewelry, you know? Explaining science. See you next time. Good night. Heike! It was so lovely that you're here in real time. I have missed you lots and lots during the real time lives. But I see your comments and they're the best. And it makes my day. All of them. There's an Indian delicacy called Nook Nook. Have you heard of it? I have not, Nicholas. Indeed, I have not. You should make it for me. I'm not really a big cook. Nook. Thank you, Heike. Thank you, Nicholas. Thank you, Neeraj. Thank you, Reese. Thank you, Lee. Thank you, Doing Something. Thank you, everybody, very much for being on the live tonight. And I will be back tomorrow, hopefully. I hope my cold is completely gone really, really soon. Thank you, Crazy Sick Wine. Lovely to see you. I need some wine. Dude, tell me some wine options, man. When I went to California, I became a member of a wine club in Sonoma. I'm actually a member at a winery that I've never since gone back to. But I learned that if you become a member, then the tastings are all free for you and your friends. Fun fact about Sonoma. Are you from California? Crazy Sick Wine. Every time I look at your username, it makes me think of wine. Now I feel like an alcoholic. But I just mainly like wine. I don't really pursue other alcohols. Not too much anyways. And I haven't had, actually been really good. I don't think I've had a drink like this month. Well, no. On December 1st I did. So Heike, I celebrated your birthday. On December 1st, I was still traveling. I went on a trip and I did have wine there. But since getting back, no, I had some wine. I did. Earlier on in December. Yeah. 24 karat gold nose ring? I don't have one. I don't have a nose piercing. Not a big fan of nose piercings myself. But thank you. Thank you so much. Indeed, for hanging out. So Heike, I celebrated your birthday without even knowing it. I was out with my friends on a trip and I had so much fun. Since then, it has been not as fun. I have been just kind of working, then I got sick, recovering, gym. But yeah. I miss wine. Instead I have to have soup. Thank you. Thank you for the soup. Ooh, thank you, Niraj, if you're still around. Thank you to my regular live stream VIPs. I hope you liked my physics topics. If you're joining late, go back into the live and look at all our discussions from today. We covered a lot of things, so hopefully you enjoy it. It's from my own thesis, so it's public information, and I can always send you a link to the full paper or thesis chapter book thing. Good soup, now sleep, come easy. Yeah, I think I'll rest. I think I'm done. I can't do real long days. I need to recover and prioritize my health. Thank you, universe. Thank you. I will rest. I need to rest. I will not talk anymore. And just rest. Please. Da da da. La 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 la. I will rest. Meditation time. 2 minutes silence. It's a theater thing where you take in. Wait, let me finish my soup. Let me talk about breathing with you guys. Okay. It's a theater thing that I learned about breathing. My nose is getting so red. I'm practically Rudolph myself. So, in theater, we learn like this. Good night. Pranayama. Release the last breath. The last little bit of the breath. Release it. Hi, Baji. Exactly. Release the breath fully. Release all negativity. That's it. Release your last bit of the breath. It'll help you feel better. Release from the tummy. We used to have to do this exercise before our theater practices, because then you can let your voice out from the tummy. You know, like in stage acting, your voice, you have to throw it out from your tummy. And it has to like work, right? Across the stage and everything. So we used to do these breathing practices when as warm up before the rehearsals. Thank you. I'm feeling much better. Let's do it more. This is my tea. Everybody, I have to breathe through my mouth because of congestion, but in through your nose. Let it out. Oh, it's called emptying your breath. Some white person told me this, even though it's probably a yoga thing, but yoga is white now. So, what do I know? You like quantum theory too, don't lie. Now, Seth! Good morning, my friend. It's all good, in balance. We will do physics, eating, sleeping, breathing, all in balance. Now, Seth, how's everything going? I had soup. Release it. Emptying your breath. Instead of shallow, deep, deep breaths. Get it out. Get it out, man. I kind of wish I had chocolate. Now, Seth, can you send me some chocolate? Some Lindor. Some Ferrero Rocher. I really want Ferrero Rocher, or however you say that chocolate name. Y'all know what I'm talking about. You do. How come none of you have ever bought me Ferrero Rocher, huh? How come? You know you should come to the live with some chocolates. How come? Good day. I want to inhale this tea. I don't really want to keep on picking this up. Should I get my straw? Okay. Anyway, y'all, lovely to see everybody. You had supper there? Your people have breakfast? Yeah. Yeah. Supper there. Yes, supper. Okay. Good idea. Did I do 6 hours? Yay. I am so happy. $9.40. I don't think so, Crazy. I see this message. Hello again, my phone's acting strange. Are you getting my messages? I see this one. I haven't seen anything else in a while. Heike, I think I'm gonna go live again like this tomorrow. And the next day. And the next day. I hope. That's what I'll do. And I'll keep talking about particle. Astro. It leaves some messages off, I seen. Well,
I think I can see most. I think I can see most of your stuff, messages, but I don't know. I don't know what's happening, crazy. I don't know what's happening, crazy sick wine. Red pants. Oh yeah, I guess I'm wearing red pants. Those are my PJs. Am I doing 6 hours? Heike, have you been seeing my clips? My name is Baji's mother. Have you been seeing my clips that are like 4 or 5 minute long? Can you see those too? Can you watch those too? That would be greatly helpful. Y'all, please watch my videos. I need the watch time in order to get YouTube monetized. What's my name really? What's my name? What is it? Baji. Baji's mother. What's my name? Coulda, woulda, shoulda. What's my name? We will rock you. Baji. Flowey, come baby. Come Shana. Fuji. I love you, my baby. I love you, baby. Touch wood and thank you, universe. Bree. Bree? Pretty Bree? Bree. I like Bree. Maybe that's my name, Bree. Maybe that's my name. Merry Christmas. Have a all the night it's my wood. I don't know what that is. I don't know that one. All the night it's my world. Is that how it goes? All the night.
It's my world. Are you guys enjoying? Okay, my voice doesn't exist anymore. My voice just went off. Okay. Are you laughing? What is this face? What is this face? Okay, I think I fixed it. What you got planned for Christmas? I'm meeting my friend. Why? Do you want to send us wine? My friend, who is currently traveling, is hopefully freaking coming back. And then we're gonna do Christmas together. Hopefully eating a bunch of fucking food. Hopefully eating a bunch of food. Mm-hmm. Oh, right on. What kind do you need, Lil? Red. Pinot Noir. Cabernet Sauvignon. Anything you can find. Something dry. Something fruity, but dry. Not too musty. Not too wet, overbearingly. Now you're talking. Yeah. Uh-huh. Not too acidic. Not too in your face. Something dry. Something that you taste slowly. Something that you can drink a lot of.